So I'm Torsten. Yes, I'm from ETH Zurich. So this is this place here in Switzerland, in case you haven't seen it. Actually, I promised one thing, and I forgot this already yesterday. So don't tell anybody. I promised to advertise this conference. So there's a wonderful conference in Switzerland. That's the PAS conference. If you ever looked for a reason to go to Zurich, Zurich is nice. Actually, only from June 12. I mean, in June and July, it's nice. Right now, it's totally sucky. It's about the same as here. So no reason to go now. So save your travel funds to go to the PAS conference, okay? No, it's actually a really good conference. I'm not trying to exaggerate. Okay, so what I'm going to do today is, as Paolo mentioned, something slightly different from yesterday. And the idea is now not to give a research talk, but to teach a tutorial style talk. So, and Paolo asked me to teach remote memory access programming and advanced MPI programming. So actually, no, it's not true. He only asked me to teach remote memory access programming, and then I added myself advanced MPI programming because I'm quite excited about it. It's a very short part. So let me just get started. Oh, actually, one thing about me. I really like teaching, but I like interacting even more. So can you please ask questions? So the more you interrupt me, the happier I will be at the end of the talk, okay? So if you have anything that is even the remotest unclear, there's also no stupid question, by the way, then just let me know, because I like answering questions. Okay, cool. So just a quick background. I don't really know what the background of you guys is, so I'm assuming it's the general computational science background. You have probably heard about MPI. I hope you have written it. So who has written an MPI program before? Oh, excellent. Very good, very good. So because I will not say anything basic about MPI. That's on Paolo's request, which is perfect because everybody has kind of worked with MPI before. Yet my first slide says MPI 1, I know. I just want to get something straight that sometimes, even for the experts, is not so clear. At least for me, for a long time, it was quite confusing when I was at your place and I was listening to people like Rolf Rabenseifner telling me about MPI. And at that time, it was really only MPI 1. So one thing is I want to get clear that MPI itself is a specification. So this is actually quite important. If you ever write a paper and compare MPI to something else in a real benchmark, don't call it MPI. Because it is as if you compare C++ to Java, which is a totally stupid idea. Because what you're actually comparing is some MPI implementation with some other implementation of some other thing. Right? You cannot expect that an MPI implementation is representative of the whole specification. In fact, each MPI implementation sucks badly. You probably know this since you've used MPI. You probably complain about these things on a daily basis. At least I do. So some MPI implementations are better than other at certain aspects of MPI. Right? So for example, MPI-CH is not so great at the things I'm going to tell you today. However, Cray MPI with the right flags is actually quite good at this. So I will talk about this later. So really keep in mind it's a specification, not an implementation. When you compare MPI-CH to, I don't know, GCC, OpenMP or whatever, you have to state this because most people don't. This is a big blunder, a really bad idea. Furthermore, MPI is a language, is not a language, oh God. MPI is not a language, it's a library. Most people also get this wrong. They say it's a programming language. It's not a programming language, not at all. It's just a silly library that you can call from a language. It's also not a programming model, by the way. We didn't put this on the slide because these slides are together with my co-authors, and sometimes they argue that it could be seen as a programming model. I completely disagree with them. It is not a programming model, okay? It is, in the widest sense, a message passing model. So because all you can do, bless you, all you can do with the thing is send messages back and forth and do some collective operations. And actually today I will tell you that you can also do memory accesses, which has nothing to do with message passing, yet it's called MPI for historical reasons, okay? So really important, it's not a language. Then all parallelism is explicit, right? So you parallelize the program, not MPI. Right, so you could argue that OpenMP is a little bit more magic. However, even that I would say is quite explicit. But MPI is even more explicit because you have to say every single thing the library does. Right? So these are the basic pieces. So then MPI 1 is basically an implementation of this message passing idea. Right? So you've probably heard about it. It's sometimes also called communicating sequential processes. CSP is the underlying theory that if you're interested in theory, you should look at CSP. Then you can find a nice formalism that MPI basically implements as a library. Right? CSP is a little bit more powerful than MPI, but you don't need that power. Well, MPI is quite old, as you know. It took quite a long time. Actually, it took quite a short time to standardize first. It took a longer time to make iterations on it, which is interesting. And now it's actually more of like a de facto parallel programming environment, as you know, or standard. So implementations are widely available, and this is also something I won't talk about. So how to actually use MPI, I'm assuming you know this, how to get to an MPI implementation. But there are many, many, many basically on every system. There are even MPI implementations for my Android phone now, which I don't know why, but somebody compiled OpenMPI as an APK. Okay, so it's free and blah, blah, blah. So cool. Then as I mentioned, it's old, so it was actually presented at SC93. That was way before my time. I have nothing to do with this. Even the MPI-2 was before my time because I was in high school at that time. So they basically, in the first iteration that I would consider the cleanest iteration, they added concepts of point-to-point collectives and data types, all the basic concepts that I will not talk about today, that I'm assuming you know. These are the very clean concepts that you find in any textbook about MPI. MPI-2 then added a little bit less clean things, in my view. So they added parallel I/O, remote memory access programming. Unfortunately, they added this stuff before they had any network available that could support remote memory access operations, which means they got it wrong. So do not look at MPI-2 RMA. It's not a good idea. It's conceptually broken in various ways that I will also discuss. They added dynamic processes, which basically nobody ever uses because they are also conceptually broken. They added thread support, which is also conceptually broken. It was fixed in MPI-3 with this mprobe. They added C++ bindings, which were later removed. So MPI-2 was not the greatest success, I would say, in that regard. So then they waited 10 years. And by the way, in these 10 years, most vendors didn't really support MPI-2. So some just said, who cares, dynamic processes, I don't need. And then this is when I started, so I was a PhD student at that time, then MPI 2.1 came, which was really boring because the whole thing they did is merge these two documents. And MPI 2.2 came that was also really boring because nothing really happened besides some new data types that were in the meantime introduced in C and C++. And then MPI 3 came, which was the major thing that I want to talk about today, the new features, which kind of came in 2012. I would say 2015 is also a very significant date. The idea here was now cleaning up MPI-2. Right? So reconsidering after 10 years what has happened and how do we actually get to MPI, to a modern MPI, so to be supported on a modern network. Right? That was quite important. So the new features in MPI-3 are basically non-blocking collectives, neighborhood collectives that I may talk about, I'm not so sure, depending on the time. There's an improved one-sided communication interface, which is, by the way, to clarify what I said before, 90% identical to the MPI-2 interface, but has some very significant changes. So they're very small from a conceptual perspective, but they really fix the way you can use it. And this is what I will emphasize on today. Or you can use it on modern network cards today. So then there was the tools interface, which I will not discuss today. If you have any questions about this, let me know. There was the addition of Fortran 2008 bindings. They're actually quite nice, but I'm not an expert at all in this, so please don't ask me anything about Fortran bindings. You can ask me about the old Fortran bindings, these I know, but the 2008 are quite complex. So then there was a huge list of smaller features like the matching probe, which, as I mentioned in MPI-2, there was a conceptual bug in the threading because you couldn't actually probe messages in a thread-safe way. This was added in MPI-3. Actually, I believe it was added in MPI-2 too. There was another helper function for non-collective communicator construction. Then there was the const correctness, com-split type, non-blocking, com-dup, which is quite useful for implementing libraries. And then a new type creation function. Okay, so and for reasons I still don't quite understand, the C++ bindings were removed. I was one of the people voting against it. However, they were still removed. And then some other functions were removed. And then MPI 3.1 added a minor piece. These were non-blocking collective I/O functions. Actually, this is maybe not so minor because the idea is now that you can have all these collective read and write functions. You can also have them in a non-blocking way, very similar to the non-blocking collectives. So this is something I will also not talk about today because usually we give this tutorial as a full day tutorial, and today it's more like a 2 hours, so about 30% of that tutorial. So if you have any questions, please ask. Okay. A lot of people are nodding all the time, so I'm quite happy. At least I get positive feedback. Okay. So if I'm too fast or too slow, then you can look at one of those 2 books here. So basic MPI, which you probably don't need because most of you have already used MPI, is this book called Using MPI, and then there's a new version, which is actually quite old, and it goes really back to MPI 1 and explains the concepts if you're a novice. If you're interested in the newer features, what I will talk about today, then you probably want to look at this Using Advanced MPI book, which came out by 2014, and the idea here is that basically explaining the MPI-3 specification to the end user. By the way, if you're an end user, you should not look at the specification. Please don't. Unless you want to become a lawyer or something. Because the thing is really written like a law document, and I don't know if you did your taxes at home the last time and actually went through this law document. They're quite hard to understand. They usually come with a guide or you hire a guide. Right? So this is the things that you should consider when looking at MPI. The specification is more like the law document that you never want to look at unless you're in some kind of lawsuit. If you can avoid it, I would look at this book because that book comes with examples, use cases, and that's in a user-friendly way, a presentation in a user-friendly way. Right? So, you probably understand why there are two different versions of this. So let me get started with the one-sided communication topic. By the way, when I talk about one-sided communication, I mean remote memory access communication. So for some reason in MPI 2 that was called one-sided because they differentiated between two-sided and one-sided, and I will discuss this in a minute. Today the more modern term would probably be remote memory access. Right? But I use these terms interchangeably. In the standard you will find only one-sided mentioned. Okay, so what is the basic idea? The idea is fundamentally to decouple data movement and synchronization. This is also the reason why it's kind of funny that it's called one-sided, because a sub-idea of that idea is essentially that it's only initiated by one of the two communicating parties. However, fundamentally, it's more about decouple data movement with process synchronization. So let me explain this. So the idea is that we should be able to access memory at some other process without the involvement of that process in a one-sided way. This also means that I cannot, if the other process is not involved, I cannot actually synchronize with the other process because the process is not involved. So how can I synchronize with it? Well, that means there are now two different kinds of functions. These are the one-sided access functions, read and write, and we will talk about them. And the one-sided, well, these are actually not one-sided, but the kind of two-sided synchronization functions. Because for synchronizing, you actually need two processes. So if you now look at this, one-sided is really only for the data access. So in this sense, I like remote memory access more because it's a better terminology. So what we do, if you look at multiple different processes here in this view graph, so we have process 0, 1, and 2, and 3. And each of these processes, by default in MPI, has private memory. Right? So this is the heap or the stack of that process. So, and when I say memory, I really mean heap and stack. So both of this is perfectly fine. In case you don't know what heap and stack is, just stick to memory. Okay, so what we can do in MPI-3 RMA is we can actually expose a part of that memory as remotely accessible memory, which is quite nice. And I will talk about this later, why this is nice, that we do not expose the whole memory, but only a part of the memory. It's controlled sharing. To just give you a primer, it's very different from OpenMP. If you run OpenMP on your computer, you will immediately share all your memory. Right? If you have a bug in your program, it can rewrite, I don't know, the code segment of your other thread, or including, which is probably also your code segment, but depending on how you program your code. In MPI, this cannot happen, because in MPI, you will only expose some memory to these processes. And of course, if you're silly enough to expose the code segment, well, then it's your fault. But if you don't do this, there is some kind of isolation for shared memory-like programming. So really see one-sided communication in RMA as a shared memory-like programming style with a way to have controlled sharing of data. And controlled is very important. So you share this memory. And basically the way you see this as a programmer is you have an array and you give other processes access to this array. Right? So that's really the way you see this. And nothing else, only that array. Actually, you can say only that subset of that array. You don't have to expose the whole array. Okay? And so this private memory, if you now look at process 0, the process 0 can access its own private memory, that remotely accessible memory of its own memory, of course. And it can access the remotely accessible memory of the other processes and not the private memory of the other processes. Right? So, and this is what we then call a global address space. So if you're now used to terms something like PGAS. So who has heard PGAS? Partition Global Address Space. So that's it's not so many. It's about 10% of the, actually 5% of the audience. So that's another programming model that we could consider. It's something that has been, the term has been coined in the context of UPC, or actually split C, a long time ago. And the idea here is that the programming model, the programming language gives you this view, right? So you program a single image, and you have kind of a logically shared global memory, which is globally addressable, but the important piece is that it's partitioned. So what does partition mean? Partition simply means that I can differentiate between local and remote memory. And now you may say, well, that's kind of clear. I can always differentiate between this. No, it's not true. Because if you use OpenMP, you have no notion of local or remote memory, even though you may have sockets and whatever involved in your system, which makes some memory more involved, more remote than others, like NUMA memory, for example. That's one of the differences. Here in MPI, we also call this kind of global address space. We could call it partitioned global address space, but MPI kind of implies the partitioning, right? So because it is multiple processes on different nodes, so there is a partitioning. So then I can read and write to these other guys. Okay, so that's the basic model. Just to look at this from a more fundamental perspective, how does it work in the real MPI implementation? So here's a small view. We have two nodes, node left, node right. We have processors here with some cores, a processor here with some cores. Then we have memory here. There are some, let's call these memory segments arrays. Okay, there are some arrays, 1, 2, and 3. Then there is a logical send queue and a logical receive queue in MPI. That you probably know because you've used MPI-1. I mean, without this view, you couldn't use MPI-1. So how do I send a message? And then there's an MPI implementation down here, right? So that's a library. How do I send a message in two-sided? Well, somehow the receiving processor posts a receive, like you call MPI receive. On MPI receive, a message, sorry, not a message, an entry goes into the receive queue. What does this entry say? This entry says that if a matching message arrives, and this is, you know this, right? I'm just formalizing it a little bit more. If a matching message arrives, and you'd specify this with a source and a source argument and a tag argument and a communicator, these are the three things that have to match, then deposit the data that arrives here in some memory segment, in some array, some address. Okay, and then at the sending process, you do the same thing, but you issue an MPI send, which now specifies a tag and a destination and a communicator, right? And then what happens is that the MPI implementation somehow magically, not visible to you, grabs the memory that you specify, packetizes it in some kind of packet, and then shoves the packet over to the receiver, then looks at the receive queue and finds out where to deposit the data. Right? So this is MPI-1. This is what you've all done because all of you have used MPI before. In MPI-3 one-sided, this works slightly differently. Basically, you have the same thing. You have a send queue, a logical send queue. It's not really called send, but for the sake of example, let's stick to this. The source MPI process grabs all the memory from the source, but without involvement at the destination, deposits the data or reads the data to the target memory directly, right? This is the difference. Very, very simple, actually. It has a lot of implications of how to actually program at the end. Okay, good. So what is one implication? So one implication, for example, is that if the target process, here is process 0, process 1, the same as before, so process 0 sends something, process 1 receives something. If the target process is delayed for whatever reason, right, it may happen that the sending process is delayed. When does that happen? If you use blocking, well, yes, sometimes, but blocking MPI send may allow the MPI library to buffer the message. So if you send a very large blocking message that is not bufferable in this sense, right? So if you use blocking communication and the data is too large to be buffered. So there's a concept that's called the eager limit in MPI, and many of you not, so you know this. So it may happen that the delayed process actually pushes the delay back, right? In MPI one-sided, this is impossible for the communication function. Of course, it is possible when you synchronize, because that's the point of synchronization to synchronize. But if you just issue a put and a get, the delay in this target process plays absolutely no role. Which is now, of course, you may now think, okay, what does my application logic do? That's then up to you, if your application logic can deal with this. But if you've been at my talk yesterday, So it's actually, for machine learning, this is quite an interesting model, right? You can just grab the data whenever and you hope that it autocorrects somehow because it mostly works, right? So for asynchronous methods, that's a very nice model. In fact, you can also use this for stencil computations. So but this is something we can talk about offline. Okay, so then I just want to make one point that this can be implemented quite efficiently, this MPI one-sided. Actually, can be implemented much more efficiently than MPI two-sided on some systems today. The reason is that every single network we have in operation today in a supercomputer style system, I have to say, so not Ethernet, supports something that's called RDMA, Remote Direct Memory Access locally. Sorry, not locally, but in hardware. So what does that mean? That this whole MPI one-sided implementation, all it has to do, it has to tell the network card, shove that data over. And the network card will fully autonomously shove the data to the destination without any involvement of the destination. If you now implement MPI two-sided on top of this network, you cannot do this, right? Because the destination address is only known to the destination. So you need to involve the destination in the transfer, which is fundamentally slower than just telling the hardware to deposit the memory into that address. There are many movements trying to implement this matching in hardware. However, there is no widely accessible product available that does that. So MPI one-sided is, for technical reasons, faster than MPI two-sided. However, that does not mean that I'm trying to evangelize MPI one-sided, so I may sound like this. But the ideal way of using MPI one-sided versus two-sided, so now after this tutorial, you know what MPI one-sided is, and you may need to decide, do I want to use MPI one-sided for this program, or do I want to use MPI two-sided, right? The way to think about this is my program fundamentally a producer-consumer program? Or is my program fundamentally a remote memory read-write program? If it's a producer-consumer program, which means some task produces some data somewhere that later another task has to read, so for example, a stencil implementation, then we highly recommend using two-sided or collective communication for that piece. If it's fundamentally a program where you, for example, have a large table sitting somewhere in distributed memory that you constantly need to read and write, then obviously that's a silly idea to do this with two-sided, because you would need to implement a server that just implements the read and write for you. So you can do this directly with one-sided. So these are two complementary aspects. If you're performance crazy today on a specific system, then sometimes you want to break that rule, right? However, you have to be aware that you may be producing code that is not portable to the next system, right? Because today, if you have a good one-sided implementation and a good one-sided system, so good one-sided systems are basically all the systems that matter for an HPC context. Good one-sided implementations is a very rare thing. But if you have these two, you can always beat two-sided today, right? So, but this is dangerous, as I mentioned, because again, you may be programming in the wrong mental model, right? But again, if you're performance crazy, yeah, so people like doing this. I have a lot of students who like this. So if you just look at the raw performance here, and this is just what I just said in words, again with data, and I'm not a big fan of presenting too much data, but here we have a specific implementation that was published at SC13, where the idea was to just show how good one-sided can be. So we implemented it on a state-of-the-art system at the time, a Cray Gemini system, which was actually the largest system in the United States at that time, the Blue Waters machine. And we compare it to all kinds of different implementations. If you just look at the latency here, it's significantly lower than, so this is our implementation, MPI-3 one-sided, 1 microsecond latency. And if you look at MPI-2, that was about 2.9 microsecond latency. So it's nearly a factor of 3 faster. You can also see that the message rate is much higher, as you can see here. So 2.5 million messages per second versus MPI-2, 0.8 or something. So there was always a factor of 3 basically involved in these differences. So just with a faster interface for small messages. For larger messages, then the difference became a wash because bandwidth is easier to achieve than latency or message rate. Okay? So then there are a lot of applications that we could show, but I don't want to go too much into detail because I'm trying to keep this more at the conceptual level. If you care about real performance, this data is valueless anyway because it's on a system that is 5 years old. So that system doesn't really exist. Well, it still exists today, but will probably not exist next year. So we don't know. So let me get back to the fundamental aspects of MPI-3, why you should know and what you should understand is really that, and this is something that is a little bit more of a philosophical nature, because just yesterday over dinner we had an interesting discussion why MPI-3 RMA is specified as it is. And there are many, many boundary conditions to this. One of the boundary conditions is, and this is probably the most significant one, it is designed to work on cache coherent and non-cache coherent systems. And by cache coherent, I mean that the receiving piece that interacts with the network and the CPU may not be coherent. This is something that is actually, there's only one architecture I know that has this feature, because it's really, really hard to program this. I don't want to name that architecture because it may cause bad feelings, but ask me in the break if you want. Okay, so for that reason, MPI is specified the way it is. So it is not specified in a way that you would, for example, implement co-area Fortran or interfaces that do not support non-cache coherent systems. So CRASH-MEM is another one. All these systems do not support this. They have much stronger guarantees than MPI. Right? This is one of the things that we have endless discussions over in the MPI forum. So nicer even is that there is actually a formal specification of a subset of the MPI-3 RMA. So if you're a model checking person and you really want to check correctness of the specification itself, but that has been done, or implementations in that specification, then you can use a featherweight specification of the semantics of MPI. So, but this is quite computer sciencey, so it's one of the things that you may or may not care about. So what do we now need to know in order to use MPI-3 RMA? That's the important piece. So first of all, we need to know how to how to make this memory accessible, right? So that I mentioned at the beginning. We need to understand how to read and write memory, right? We need to understand how to synchronize, and then at the end, if I have time, I will talk a bit about the memory model. The memory model is rather complex, and I will not be able to explain it in the time available. However, I want you to know that it exists and it's non-trivial. Okay, so we start from the simplest and go slightly harder. Right? The hardest one is the memory model. So the simplest is basically, how do I create memory? Okay, how do I create memory? Well, how do you create memory in a C program or a Fortran program? Well, you either ask the language to allocate some memory for you by a variable specification, right? It usually goes on the stack if you ask the language, or you call a library, the malloc library, or a new constructor in C++, or an allocate in Fortran to give you some memory in the heap, right? And usually it comes back at an address, and you assign the address to a name, and that's then your variable that you use in your program. So once you have this memory region allocated on either the heap or the stack, again, it doesn't matter for MPI, then the user has to tell the MPI library that that allocated memory is now accessible, or should now be accessible to remote processes, right? So for reasons I don't want to explain, remotely accessible memory is called a window. You can remember, if I'm looking at a window, I see a limited view of something, and this is really like you have to imagine you stand outside and look into somebody else's apartment. And so that's kind of the mental model, right? You have a window that was created by the process to enable other processes as a restricted view on your local memory, okay? So, and then what's very important is that actually a window is created for a group of processes, so a collection of processes, so a communicator, basically. But a window always has a group associated with it. For some reason, for MPI technicalities, it's not the communicator that's associated to the window, it's the group that is associated with the communicator. Right? So if you're an MPI lawyer, again, then excuse me if I say MPI window has a communicator attached. It's really a group. Okay, so then once a memory region has been declared, like here, as publicly accessible, all processes in the group attached to the window, in brackets the communicator, because you never see the group. Most of the users never see the group. Then you can access this from all remote processes. Right? There is no further containment domain. It's just publicly visible to everybody, to every process in that communicator. Okay, so how do I now create this? And as usual in MPI, there are multiple calls to achieve the same thing. However, you will need all of them. You may need any of them to write a useful program. So the most useful one in my view is MPI win allocate. Why is that the most useful? And this is a new one in MPI-3 that did not exist in MPI-2. What does this function do? In fact, it does two things at the same time. It allocates the buffer, so it'll actually call the let malloc for you. So you don't need to allocate that buffer, and at the same time exposes it. Why is that good? Why should the MPI library allocate memory? Well, the reason is that it could choose a specific location for that memory to sit at that is globally the same, so it saves itself translation tables. That is quite powerful. Very, very powerful, in fact. So if you can do this, let the MPI library allocate your memory, because it'll do it better than you can. Right? So the second one is MPI win create. That is if you already have a memory buffer that you want to expose, or if you want to share a variable on the stack. So obviously MPI win allocate cannot work with variables on the stack. Right? So if you have an int a that you cannot MPI win allocate, we should be doing this anyway. It's one of those things. It may not be the best idea to do, but you can. MPI win create, you can take memory that already exists and expose it to other processes. So you could take your int a and expose it to other processes. Nobody would do this in practice. Then you have MPI win create dynamic. The idea here is that this creates a memory window that has no memory attached, and you can later locally attach memory. So all of these calls here are actually collective on the communicator. Right? So which means every single process in the communicator has to call these calls logically at the same time. Right? This is very problematic if you have a program that locally creates new tasks and new memory and doesn't want to synchronize with everybody else every single time it creates new tasks and new memory. For that case, you can use MPI win create dynamic. Be warned, this is the most expensive function you can have to allocate memory. This function requires the MPI library to keep translation tables for every single memory region that you allocate later. So it is quite expensive to access those. Right? This is the cheapest one. This is the next better one, kind of. This is the most expensive one. The last one is kind of special, because the last one is quite cool. It can be used to allocate memory for processes in a shared memory domain. So you can actually allocate kind of a strange window that points to the same memory if you're on a multi-core node. So in a multi-core node, if you have 4 cores and you run 4 MPI processes, you have no notion of sharing memory in MPI-2. MPI win allocate shared allows you to create memory that is identical at all processes, so shared memory, essentially. So you can read and write to share large tables or whatever in your processes. Right? So that's quite an important function. That was basically the main reason, or one of the main reasons, why many people used OpenMP in large physics applications, because they had large tables that they didn't want to replicate between all MPI processes on the same node, because they were read-only tables anyway. This you can do in MPI-3 very easily to have one of those global tables. Okay? So let's get to the first function. I will have a lot of these functions on the slide. I don't want to spend too much time on them. So I will just glance over the interface, but again, this is something that you can look up at home. I really want to just get you the concepts, that you understand the concepts, not the interface. I will only talk about C interfaces and not about Fortran interfaces, but they're very similar, the Fortran interfaces. Okay? So MPI win allocate, what does it take? It accepts a size. By the way, MPI a int is called an MPI address integer. So that's an integer that is large enough to hold an address on the architecture that you work on, because you may be working on 16-bit thumb ARM architectures, 32-bit, I don't know, old x86, and 64-bit x86, 64. Right? So the MPI will magically figure out what the right size for that type is, and you should make sure that you actually use that type, because if you use MPI int, it may go wrong, because MPI int is allowed to be smaller than MPI a int. Right? So, and then it'll just cast away parts of your address, which is not good. So then you can specify a displacement unit, which is quite of a yeah, this is something that's for convenience. It's quite nice because it allows you to remotely address non-integer, non-byte-sized elements. So basically what it does, the remote address space is exposed to you as a linear array. Right? So it has a remote offset 0 to remote offset n. But if you now put integers, let's say 32-bit integers of size 4 byte, so 32-bit equals 4 byte, right, at this destination, then you would always need to say, well, the first integer is at byte 0, the second integer is at byte 4, the next one is at byte 8. So you would always need to compute the right address like you do in C. In MPI, they thought, this is an MPI-2 thing, that it may be very convenient to just say, well, the displacement unit is 4, and when I'm accessing element 2 of the buffer, I will go to address 8. Right? So that's just a convenience thing. So it always will just multiply the address by this number. And it's very, very trivial. So then you can specify an MPI info object. That's something I don't want to talk about. So these are additional hints to the MPI library. You can look them up if you want. Some of them are extremely useful, and I will mention some of them, but not in detail. Then you need a communicator, as I mentioned. You will need this pointer that you actually get back, right, because it's the allocate function. And you will need an MPI window that you will, window handle that will be returned to you. Okay, cool. Just to look at an example, we have an int main function, takes the arguments, blah, blah. We have a star A, which is our array. We have this MPI window. We call MPI init, of course. Then we call MPI win allocate. We create an array of 1,000 integers. We want the displacement unit to be integer because it's an integer array. We give no infos. Of course, the C interface still forces you to put some argument. So we have a blanket info argument. We use MPI convert, which is one of the things that you shouldn't be using if you're a good MPI programmer. Right? However, for this short example, I'm using this here. And we specify this array A as a return. And we specify the window as a return as well. Okay? So then this array A is now accessible for to all processes with the functions I will be discussing in the next couple of slides. And then we free the window with MPI free win. Again, if you have any questions, let me know. So so who thinks that I'm going too slow and I should be going a little bit faster and I'm too basic? Okay. Who thinks I'm too fast, I should be a little bit slower? Okay, I need to go a little bit faster. Very good. So then we have this MPI win create call that I mentioned. We have this base pointer. We have the size, displacement unit, info, communicator, and window is basically the same as before. It just doesn't allocate something for you. It just takes an already allocated address. Right? If you have an example with MPI win create, it's basically here. There's already memory allocated. For whatever reason, for this example, we are using MPI alloc mem. We could have used malloc here. Right? So there's already memory in this int A. And it basically looks the same at the end, right? The int A is an input argument and not an output argument here. Okay, cool. Creating dynamic windows, as I mentioned, there is no memory associated with a dynamic window by default. So we have an info argument, communicator, and window. That's all you do. Once that function returns, you have 0 bytes associated with that window. Okay? However, there are 2 functions that you can call, win attach and win detach, where you can attach memory regions to that window. So you malloc a memory region, and then you can attach it to that window with MPI win attach, and then you can later detach it from that window with MPI win detach. By the way, you always must be sure that you do not deallocate memory while it's attached to a window, because then you'll get a seg fault. It's also pretty clear. Okay, cool. So here is MPI win create dynamic example. We do this win create dynamic here. We do win attach. Now we attach the 1,000 integers ourselves, and then we do a detach and then an MPI win free at the end. And here is also a free. Now we use malloc here.
What happens if you attach windows of, buffers of different size?
Oh, that's perfectly fine.
That's
yes. And now you may wonder, what's the addressing scheme? Because before I said that in a normal window, the addressing scheme is offset 0 to n. Here, the Windows base address is MPI bottom. So now for addressing these basically random memory things, we need to work with the addresses relative to the absolute 0. The absolute 0 in MPI is not really defined. You may think in C. C starts at the address 0 and goes in a linear address space. It's not true because C has segments. Right? So there may be different relative addresses in there. This is why the reference is called MPI bottom. So when you work with this, you have to query what MPI bottom is, and then you can do address arithmetic on this. It's slightly more complicated than before. But if you use this, you are an expert. Right? You know all of this. Right? So you should not be using this without reason because it's so expensive.
Win attach and detach are load operations.
Yes.
Not like
Correct. Correct. Only this create dynamic is a collective operation and free, but detach and attach are just local. It's basically like IBV register memory or something like this. Right? Okay. By the way, these functions are necessary. You now may also wondering, why is there not a function that I can just say, hey, expose my whole heap? Right? that function does not exist for technical reasons because the low-level network interfaces may require registration functions from you. Right? So InfiniBand, basically every, no, not every, n-1. Blue Gene does not require it. But everything else, okay, Quadrix does not require it, but both of them are dead. So both of these architectures don't exist anymore. All architectures that you can buy today require you to register memory. Okay, any other questions? Very good. Okay, so then we know now how to use, how to allocate memory. Let's now get how to move data. So there are many, many different functions how to move data. Put, get, accumulate, compare and swap, and fetch and op. However, they are very, very simple, so I will be rather brief here. So the MPI put function is really a function where you can just put some local buffer to a remote memory. Right? It couldn't be simpler. What you do is you take an origin address, basically that's my local buffer offset 0, an origin count, that's the number of elements I want to send from my local buffer, a data type, that's the same as your MPI send thing, right? That's what data type they are of. And then you specify a target rank, and then you specify target displacement, which is now relative to the offset 0 at the window I just created at the target, a target count, and a target data type. You see that there are two data types involved now. In an MPI send, you have one data type, and in an MPI receive, you have another data type. Here, you have in the same put call an origin data type, which is the local one, and a remote data type. Now I see some faces lighting up, and it's like, yes, if you know data types, you can change data layout from origin to target. Right? You can, for example, transpose an array on the fly, or you can ask the MPI library to do this. Depending on the quality of the implementation, this may or may not be fast. Okay? But you can do it. You can specify arbitrarily different data types. Of course, the type signature has to match. Right? You cannot transform floats to integers or something like this, but you can change the layout of the data, which is quite powerful in the sense. Okay, so then MPI get is basically the same thing, but the other way around. Yes?
So if you create a window collectively an MPI convert,
yes.
MPI create element.
Mm-hmm.
So basically every process creates this buffer
Mm-hmm.
for the window.
Yes.
And if I do a put, I put it basically in every other process.
No, you put it at the target rank.
At the target rank.
Yes, yes, you have to select one process. There is no collective put. Now, you could think about a collective put, like put it to all processes, but that doesn't exist in MPI.
Why?
Because we didn't get to it. I proposed this at some point, and everybody was like, oh, we were so busy. And then eventually we didn't get to it. And it's another issue, actually. If you look at the semantics of collective operations on one-sided data, they get wanky. Because you will see soon, if you don't already know, the synchronization problems that we will have. This is just putting data without synchronizing.
Can I attach multiple buffers to a window?
Yes, with dynamic.
Okay, so how do I choose which, where do I put the data then in these different buffers I have?
At the target displacement.
So I get, how do I calculate that? So I have the MPI button with the address for
Yes, that's my 0 address.
for a specific buffer that I attach. And how do I choose which one I want to have?
So what you do is you do MPI get address MPI bottom. You do MPI get address your buffer. You subtract the 2, and then you have your offset. And the buffer you just address, and you have to query this through MPI get address because that's the only way to get the correct segments. I know in practice nobody uses segments, but if you want to write a portable program, then you have to do this. Does that make sense? And that's now your remote address. You then send this address to the origin, and the origin uses that as the displacement here. Okay, cool. So MPI get is the same thing. MPI get, it's just that the origin is now written to. Right? So I'm reading from the remote node. So I'm reading the blue stuff into the green stuff. Here, I'm reading the green stuff into the blue stuff. Right? It just changes the role. It's a read versus a write. And I don't think I need to explain more. It's clear to everybody, right? Okay, cool. Now it gets slightly more complicated, but not even. It's still very simple. We could now say that we want a remote read-write. So we want a remote atomic operation, which is quite powerful in practice for many algorithms. So the first one is called accumulate, which is also the original one for MPI-2. As I mentioned, it's about 90% identical. So in MPI accumulate, it's the same interface as we had before. Hey, it's the same as get, the same as put. There is one thing different, that's the MPI op. So we have a source buffer, which is all the green stuff. We have a target rank, which is the first black one. We have a destination buffer, which is all the blue stuff. And the only difference that we have now is the op. Right? So what is the op? The op is a predefined operation that MPI specifies, where you can say what should happen. So for example, one op is MPI sum. So you could say, please add the source buffer to the target buffer atomically. Right? So if the target buffer is 5 and the source buffer is 3, and I do an MPI accumulate with the op MPI sum to the target, that'll be 8 after the operation at the target. Okay? Very simple. There are many other operations, MPI prod, MPI or, MPI replace. So, sorry? Correct. The atomicity, okay, very good point. The atomicity is element-wise. So if I put origin count 2 from 2 different sources, I may get an arbitrary order of the operations for the 2 elements, which is okay for associative and commutative operations like sum on non-floating point values, product, or many others. It's not so okay for MPI replace, because MPI replace is not even is not associative, right? Because the last one will be replaced. MPI replace literally means replace the value at the destination with whatever I have. If I do this from 2 sources at the same logical time on 2 integers, the result may be the first integer from the second source and the second integer from the first source, or all the combinations of the sources. Correct. MPI replace is equivalent to a put. However, in the MPI memory model, it is illegal to issue 2 puts to overlapping memory. I will talk about the memory model later. But if you, at the same logical time, do 2 puts to the same destination, the MPI library may write whatever data it wants to the destination. So you put 5, the other one puts 6, and you end up with a 255. Right? So that's a perfectly legal behavior. It's very similar to the C memory model. As soon as you have a race condition, right, which you probably know, the C++ memory model, as soon as you have a race condition in your code, the code may go and delete your hard drive. Right? That's a perfectly valid behavior for that C++ violated or C++ race. Here in MPI, it's similar. The code may go, or the MPI library may go and erase your whole window or something like this. Right? So, right, keep this in mind. I wanted to talk about this later, but since we have a question, very good. Keep with more questions. So MPI replace is the hack for this, Simon. MPI replace makes it legal to have overlapping puts. Remember, you don't get any guarantees for more than data type atomicity. However, it's quite useful. It is really useful. MPI no-op, well, MPI no-op is another one that is totally useless for MPI accumulate. Right? So because what do? I accumulate and don't do anything. We will see in a minute why this is very useful. Okay, good. So here it already says op MPI reduce implements an atomic put.
So it
right?
just keeps the value that was already there. If you do a no-op.
In a no-op, you don't do anything in a no-op. For this operation, I mean, doing a no-op, you can as well remove the operation. It doesn't do anything. Right? However, get accumulate is now quite useful, because get accumulate is the same as accumulate, but it gets the value that was there before into a local buffer. Right? And now if you use a no-op, you have an atomic remote read or an atomic get. Right? Down here. And you can also use an atomic swap now if you use MPI replace as an operation. Right? So now you can implement very nicely full atomics basically in MPI-3. Okay? But now you may be a little bit annoyed, because if you want something like a compare and swap operation, so you're probably all familiar with compare and swap operations, and these are, I think, 13 arguments you need for a single compare and swap of a single 64-bit value or something like this. So that's not a good idea, because just parsing these 13 arguments is more expensive than issuing the actual operation. This is why there are 2 helper functions, convenience functions, I would say, not helper, that take special cases of MPI get accumulate and reduce the number of arguments, okay? Because just to make it fast, otherwise there's too much argument parsing involved. So one is fetch and op, which you can implement with MPI get accumulate, right? However, fetch and op says I use a single data type. A single, actually basic data type. And then I have just an origin address, result address. I have no origin data type, result data type, and all these things. And target displacement and an MPI op. So this is kind of a shortcut if you don't want to specify all these arguments like counts and whatnot, right? So, well, you can use an MPI-derived data type. However, in the most common case, you want to use a basic data type. I know no algorithm that will use a non-basic data type because you still only have element atomicity. If you had full access atomicity, then it would be very useful to use data types with 2 because you could implement a double compare and swap, for example. But with this, you cannot because you will only get element atomicity, so it'll still commit interchanged and doesn't make much sense for this. So the only real use case for this operation is to use a basic data type. Or maybe you can come up with something else, but I would be interested to hear what that would be. Okay? Good. So then we can have MPI compare and swap, which is also kind of a shortcut operation. And this is now basically take the origin address, the compare address, the result address, and then the it's basically like a compare and swap in C. So there's not too much to explain. I don't want to bore you by reading all these things. So remember, fetch and op is a simpler version of MPI get accumulate. Compare and swap gives you one more. You cannot implement compare and swap in terms of get accumulate because it gives you this compare address. Right? You could if you had user-defined operations in op, but we don't have user-defined operations in op yet. Right? So it's not that powerful. It's not as powerful as collectives, for example, where you can specify your own operation. You cannot do this in, yes? The reason was basically that we wanted to make sure that any network card can implement these operations very swiftly. So we recommend to vendors that all these operations, which is a very limited list, there are like 16 or something, should be supported in hardware, which is not true for any vendor that we have today, but most of them are. And in fact, we could argue this. We should probably have standardized these things. But once you do this, it's really hard to implement it in a truly one-sided fashion. So for this interface, I could argue with a vendor saying, this is the way you implement it. As soon as I allow user-defined operations, then I would tell the vendor, now you need to implement something that downloads your handler from your program into the NIC, that the NIC does it, and then it's possible, but quite hard. Next generation. Okay, cool. So this is actually what we are working on in research right now, trying to, how do we offload handlers to NICs? So that's still a very active research topic. Okay, cool. Now it comes to interesting stuff. So if you have been bored until now, looking at interfaces, then it gets interesting. So this is what I just answered to the question. So what is the ordering of these operations? There is no guaranteed ordering for put or get operations. In fact, as I mentioned, overlapping put or get operations are illegal. Right? So they can commit in any way, and there's absolutely no ordering. So which basically means the result of the concurrent put to the same location is undefined. I'm not quite sure, and I would need to review the spec again, exactly what we decided on whether 2 overlapping put operations can change the content of the whole window or not. At some point, we had the discussion that they could actually change the content of the whole window, because if you flush a cache line, you may flush neighboring elements. But I'm not quite sure, so that would need to be checked. And I can check it if you're interested. So then, a result of a get concurrent with put accumulates is also undefined. Right? The only thing that is defined that on overlapping memory locations is if I'm only using atomic operations. So get accumulates, or compare and swap, or fetch and op. Right? So the result of concurrent accumulate operations to the same, as I just mentioned, is defined according to the order in which they occurred. Now it gets interesting. What is the order in which they occurred? So now the problem is, I'm not sure how well you're familiar with memory models. I teach this, and it's usually 4 full lectures, 4 full 90-minute lectures to understand memory models. So I'm trying to make this very short, but this is not simple, because you have an issuing order. Each process issues these accumulate operations in a specific order, right? The program order. Like you see the first accumulate, then the second, then the third, and then the fourth. And in MPI, by default, it will commit in the order that you specified. However, if you want, you can relax that order to make the implementation faster. By default, it's the slow path. It's what we call the principle of least surprise. The problem is with memory models, you will almost always be surprised if you do anything. So we try to make the least surprise. So there will still be surprises, but less surprising than you think. Because a relaxed memory model would actually mean that the library can permute the operations. You could issue an MPI put A equals 1. After that, an MPI put A equals 2. And then later, you read A equals 1. Right? By default, that's not the case. Okay? By default, if you don't change anything, you will actually read 2, the last written operation. Okay, good. That was only true if you do these puts from the same source process. If you do them from different processes, there's of course no ordering. Right? Okay, good. So this is what I mentioned here. Accumulate operations from a given process are ordered by default at the destination. This is something that's quite important. And the problem is most people don't understand why it's that important, because they naturally assume that they're always ordered. If I have line 1 first and line 2 second, it's clear that line 1 is executed before line 2. It's not so clear if you talk about memory models. It may interchange. But MPI is fine. If you're the total expert and want the latest, greatest performance out of your network, as I mentioned, you can relax this memory model. You can tell the MPI library, I do not need this strict ordering, but you should only do this if you're absolutely sure. And then you can say, well, you know, I do not want read after write, write after write, read after read, or write after write ordering. So you can basically say, I do not need any of these orderings, or I need an arbitrary subset of these orderings. Right? This is only for experts. So most likely you won't care about this. It's very similar to the C++ relaxed memory model. By default, the C memory model is very strict, or C++ and C99. And you can relax it to specific operations in a very similar way as here. But then there are many people who say that it's impossible to program afterwards. I would agree. So know that it exists, but don't necessarily do it. Okay, cool. So now in case you haven't been able to fully follow this, and this is probably my fault because I explained it without a picture, let's go through a detail. So to 3 examples. So we have concurrent puts. So concurrent puts, they have process 0, process 1. We have a put x equals 1 to variable p1 and a put x equals 2 to variable p1. Right? The value here is basically undefined. Right? It could have anything at the destination. So if we now have a concurrent get and a put and accumulate, so for example, we have here a concurrent put and the concurrent get, the value is also undefined. So basically that get here could read anything, right? So that would be a perfectly valid behavior. So then if we have 2 atomics, get, accumulate, and accumulate, that are actually also writing the same value, p1 here. So for example, we have get, accumulate, y, and we say x plus equals 2. So we read x plus equals 2 into y, and we have an accumulate x plus equals 1. There is the guaranteed ordering that this get, accumulate will add this 2 before the accumulate will read, or sorry, before the accumulate will add this 1, right? So it'll definitely happen if x equals 2, it'll definitely first see the addition of 2 and then see the addition of 1 at the destination. So whatever is read, if another process is now atomically reading these values, the process can read x equals 2 here, x equals 4 here, or x equals 5 here. It could never read x equals 3, right? If you relax the ordering, as I mentioned before, the process could read x equals 3 at some point. Okay, is that clear to everybody? Good, this is basically this memory ordering. And again, if you don't fully follow, then there is a large part in the book that I mentioned, but it most likely won't concern you. So it's one of those things you should know, but it may not be important. Okay, very good. Now we discussed how to actually read and write data, how this data is ordered, what are the valid conflict things that you may have there, and now let's talk about the synchronization, which is the last piece of the fun that we have with RMA. So we have the RMA data access model. Basically, we read, what does that mean? When is the process allowed to read and write remotely accessible memory? So we somehow need to tell the remote process it's ready, and now you can read it, and when you have to stop reading it. And the other question is, when is the data written? That's that I'm writing, for example, process X, when can it be exposed to another process? And the synchronization model is the way you define how that happens, right? So then, and there are basically 3 synchronization modes, and all of them existed in MPI-2. Again, as I mentioned, it's 90% equivalent. However, the last one was heavily extended in MPI-3, and this is what I will focus on most. Actually, the synchronization models are quite elegant, I have to say. So there's fence, there's post-start complete wait, and then there is a lock-unlock. First, let me get some terminology right. So the terminology here, the most important term is called an epoch. What is an epoch? An epoch is a region in the execution of a program between 2 synchronizations. Okay? There are now different types of epochs. There is an access epoch, and there is an exposure epoch. So an access epoch means if I am opening an access epoch, then I'm saying I am now starting to read and write remote memory. So I am the origin of accesses. Okay? That's what an access epoch is. I have to start that access epoch. Then there is an exposure epoch, which is basically I am now exposing my memory to be read and written by remote operations. So these are 2 different things, right? For the access epoch, I'm the origin. For the exposure epoch, I'm the target. Okay? This is very, very important to get this. Then these epochs, they define everything with respect to ordering semantics in memory. That is ordering between local reads and writes, so loads and stores of the CPU, and remote accesses. This is quite important. So we just discussed the ordering semantics that we have between accesses through the MPI library with puts and gets, but I didn't tell you how this relates to read and write of variables coming from the local CPU. Right? This is what's defined through epochs. Okay, so and then these synchronization models, they basically tell you how to open and close epochs, like access and exposure epochs. That's all I will be explaining in the next couple of minutes. So start and end these synchronization epochs. Okay, so the easiest one is fence. Fence is totally trivial. So what does fence do? It's a collective operation, right? First, so everybody calls it. That's why it's so simple. Basically, the state of the epochs across all processes is the same. A fence doesn't even differentiate between access and exposure epochs. A fence opens and closes access and exposure epochs at the same time. So it goes from one epoch to the next. Always the whole thing, right here. So all these processes, they move. So what this basically means that within an epoch you can read and write remotely. I mean, sorry, I should have said put and get, and accumulate everything. But you can never locally read the results of these operations in the same epoch when you issued the operation. Okay? So what you do is you do put get, then you issue a fence, and after that you can now access the variables that have been communicated. Right? That's the important piece. They need to be in different epochs. Right? This is the way you synchronize with your local CPU. So this is the simple one. And do I have anything on the slide that I didn't talk about? No. So it's basically really, it's a very simple operation. So if you look at a stencil computation, which probably most of you have seen, so we have a halo exchange. So here are 9 processes, 0, 1, 2, 3, 4, 5, 6, 7, 8. And there is an inner region. It's a 2D stencil computation. There's a halo zone, which we expose. And for simplicity, there's actually an example code that I don't have time to go through, but I will make this available to Paolo, who can send this around, where you can look at the code and actually play with the code and implement it. If he had more time, I would love to do this, but not enough time. We expose the whole thing, and we have now an exchange from the origin buffers, which is the halo zone in here, to the target buffers, which is the yellow or the green piece here, right? So, and you do a put to all your neighbors, and then you do a global synchronization, right, with a fence. This is an extremely inefficient version to implement a stencil, right? You wouldn't do this in practice, but it's good for exercise. So, and it's in this code. The problem with this is, and if we were going through the code, I would now explain why this is silly. So, can anybody maybe tell me why this is silly to issue an MPI win fence after I have performed these puts to my neighbors? Anybody? Yes?
You also want to receive the halos from the other.
Well, so yeah, the image is incomplete. So basically all the processes would do the put. Yeah, I'm just showing the middle one, but all the processes put to their neighboring nodes, but it's still silly to issue an MPI win fence at the end. Well, okay, it may not look silly to you because that's the only synchronization operation I told you about, so you don't know anything else, unless you've heard this before, but then you probably wouldn't be here. So the problem with this is that I'm only communicating with 4 processes. Each process communicates with at most 4 processes, right? But when I'm issuing an MPI win fence, I am synchronizing with how many? With everybody in the window. So if I'm running this on 1 million MPI ranks, and I'm not kidding, we are running 1 million MPI rank jobs, right? Then you synchronize with 1 million processes, even though you only need to synchronize with 4. And of course, synchronizing with 1 million is much more expensive than synchronizing with 4. So for that specific case, there is another synchronization mode that's called the post-start complete wait, or sometimes the general active target synchronization. But general active target is again one of those terms that is hard to remember. I always remember it as PSTW, post-start complete wait, because these are the operations you need to issue in order to make it happen. This is one of the most complex synchronization modes that took me the longest time to understand, but it's extremely powerful and super elegant. So it's worth understanding. However, unfortunately, the implementation is not always the best in MPI implementations today because it is so hard to understand, I guess. Okay, but let me try to do it, to introduce it nicely. So like the fence, it does the same as a fence, but the origin and target now specify who they communicate with, and that's very important. So the fence basically says, I am synchronizing with everybody, with the whole world. And here I now say, in post-start complete wait, I say, well, you know what? I know that I only send, or I only put and get it, I only issued put and get operations to the following 4 nodes. Node 5, node 6, node 8, and node 10. Why don't you only synchronize with these following 4 nodes? Why do you not synchronize? I mean, why should you synchronize with everybody? This is exactly what you do. So you have to do 2 things. The target has to start an exposure epoch, obviously, because it needs to expose the memory to the destinations or to the origins. The origin needs to start an access epoch, as I mentioned before. Right? So we now have 2 different calls for each. Win post starts an exposure epoch. Win wait closes the exposure epoch. I do not know who picked these names. They're quite confusing. They should actually just be called like start exposure epoch and end exposure epoch, but it's called post and wait. Okay, but post, you could imagine I'm posting it on some board. Here's my memory, and wait, I'm waiting for the processes to be done. That's the way you could remember it. The access epoch is exactly the other way around. I'm basically calling win start. Okay, I'm now starting my accesses, and win complete, I'm now completing my accesses. Okay. So what do I do here? At the target, I'm starting my post, which synchronizes with the start at the origin. Right? So in win post, I will actually specify an MPI group. That means I'm exposing my memory to these X processes. So for example, 4 neighboring processes. In the win start, which has exactly the same interface as win post, I'm doing the same. Of course, these groups have to match. Right? If they don't match, then it will not work. And in the win complete and win wait, what I just do is I'm closing the access or exposure epoch that I started before. Okay? Very simple. So in this sense, the post synchronizes with the start, or in other words, start waits until the respective post has been posted. And here it's the other way around down here. The wait waits until the respective complete has been posted. Right, so time flows down here. And then I do these accesses. Okay? You look like you have a question? No? Good. This is somehow the more complicated synchronization mode. The last one, the nearly last one, is quite simple. If you know what locks are, these are locks. Actually, they don't really behave like locks. That's a bit of the problem. So don't get confused by the name. And I will explain this in a second. So we have, so this was called, by the way, active target synchronization. And this fence is also an active target synchronization, to just make this very clear. Fence is an active target synchronization because all the targets are actually participating in the process, right? They all call it collectively. The PSCW is called generalized active target synchronization because I can now specify sets of synchronizing processes. Yes?
So the wind post is a collective core?
No, it's not collective. Sorry, it is collective, but the groups can be sparse.
So if you go back to the picture.
Which one?
So the middle one would post a group containing its 4 neighbors.
Correct.
Okay.
And it would open.
The other one would have a group, MPI group of its neighbors.
Correct.
And for
and the neighbors have to match, right? So this has to, when this posts something, it has to specify that process, and that process, right? And when this guy starts an access epoch, it has to specify these other processes, so they have to match. The post and start groups have to match. Okay? Otherwise, your program may deadlock, or will deadlock probably. Yeah. Yeah, in this case, I would actually do neighborhood collectives. I agree. It is. I just want you to know what that is. I would myself not use it.
And the complete is on the whole window. So I did my internal exchange.
The complete closes the access epoch. Yeah.
Okay.
And the wait closes the exposure epoch.
Would it be a third argument?
Then you can specify certain things that you don't have overlapping or something. I forgot exactly what assertions, but it's like an assert is like a fast info argument, because info arguments are strings, and you don't want to parse strings in these functions because you call them very, very rapidly. Okay, any other questions? And again, this is expert knowledge that probably most of you would know. Lock unlock. Now it gets hotter. So this is now the first passive target synchronization. And this means that the target is actually not involved at the synchronization, which is quite funny because how do you synchronize with a target that's not involved? It's kind of weird. But it's basically, I can lock a target remotely without the target knowing that it's locked. Right? Well, this is kind of logical. So I just lock you in, but you don't know unless you check whether you're locked in or not. So it does not really participate. So in this sense, we issue a lock here for that process, and we later unlock that process, but that process doesn't know it, right? Unless the process itself tries to lock itself, right? Then it, of course, may realize that it's locked, but otherwise it doesn't. So there are very simple functions, MPI win lock. So there are different types that you can choose. There is a shared and exclusive, which are basically reader and writer locks, right? A shared lock is a reader lock. Exclusive is a writer lock, but they're named more generally here. You lock a specific rank. You again have an assert, and I forgot exactly what the assert could be, but you can check the documentation. And then you have a window. So for an unlock, you unlock a rank and a window again. Okay? And it does what you may think. Actually, it's a bit more complicated because it doesn't actually have to lock the target. It has to behave as if the target was locked. So it is a valid implementation to implement that whole lock mechanism on top of something like transactional memory, where it doesn't ever lock anything. As long as everything issued between lock and unlock is happening atomically. This can cause quite some confusion if you really think you lock something. For example, if you think you can use these functions, lock and unlock, to synchronize two processes by locking a third one, no, you can't. So it should really be called transactional memory. And this is one of those things, but yeah, we can change the names. So remember, lock and unlock is somehow makes all the operations between lock and unlock commit atomically at the destination. Okay? That's the important piece. Okay, cool. So it behaves like a lock really. Then we have flush, which is actually even more interesting. That was introduced in MPI-3. So what we can do here is we can make sure that while the operation is running, the lock and unlock is running, the remote data is visible. For example, if I have a shared lock type, because in an exclusive it doesn't matter because I'm the only one who can see that anyway at that time, so I don't need to flush. But if I have a shared, other processes may grab the same shared lock at the same time. Right? and I may want that they see what I have written to the destination. Usually, if I don't do shared, that value written at the destination is only visible after the MPI unlock, right? But I can force it to be visible with an MPI flush at any time. When the flush returns, it's guaranteed that the value is visible to everybody involved in the window at the destination, okay?
But again, it flushes all outstanding.
Yes.
method.
Everything that you issued before. Like if you do get, put, after the flush, these gets and puts are complete. In formal terms, you would say it closes the access epoch and reopens the access epoch, right? So it does an epoch switch. However, it's not really specified that it does that because there's a bit more involved, but you can think about it as that. So let me get to the next one. What I would not recommend using this at all. Okay, so this is the history. What I would recommend using is something that has the worst name ever because it's called an MPI win lock all and it doesn't lock anything. Right? So MPI win lock all is quite a funny name. It should actually be called MPI open passive access epoch. That would be the right name. So what does that do? It opens an epoch from you to all other processes in the window because in a lock you only lock one process. Right? But here, you lock essentially all processes in shared mode because it doesn't make any sense to lock all processes exclusively because then you're immediately deadlocked if you do this, right? So it is shared by default. So it also has this assertion and a window and shared by default, and you have an unlock all, of course. But what this now means, and this is the coolest MPI RMA programming model. So this lock all allows you to basically program like OpenMP shared memory style. So what you do is you just lock the whole thing. Every process, what I always do is I do a lock all on all processes, and then every process has a full access to the full thing, and then you just issue get, flush, get, flush, get, flush. And it's getting a very intuitive programming model because you now issue your gets, and when you want the result of the gets, you just flush. Right? So it's really read, synchronize, read, or write, synchronize, write, synchronize. So this is the shared memory mode for MPI, and this is the model that everybody should be using, in my view, and again, I'm very biased here. The general active target synchronization is well, you should be using neighborhood collectives if you want this, and the fence mode you only use if you have a very dense access pattern for graph computations, for example. There are some cases where you want fence, in fact, but this one is the most powerful one.
I can see that this solves the works in the get flash, but I don't see the put flash when different neighbors put.
Well, okay, so when you think about different neighbors, you probably think about consumer-producer synchronization. So you have a neighbor that puts something to me, and then I want to read it. Is that
no,
the use case?
Thinking when I have, again in the stencil, when different neighbors put,
yes.
now in the stencil they put into independent parts, but what if they were writing actually in the same?
Yeah, well, that doesn't work. You have to make sure that they never write, well, unless you use atomics. You have to make sure that they never write into the same location.
Oh.
So that's, it is, but it's very much the same on OpenMP, for example. In OpenMP, if you're writing to the same buffer and it's not aligned, you may get arbitrary outputs. Right? So this is a model that's very, very similar to shared memory programming in all the ways. And in fact, OpenMP also has a flush operation. It's just that most people don't talk about it because most people don't understand the memory model of OpenMP. In OpenMP, strictly seen, if you want to read something, you also have to flush. Somehow it magically works most of the time because eventually the CPU will flush it for you. Right? CPUs are quite rapid at flushing, but there are some CPUs that don't. And then you have memory ordering issues. And here it's exactly the same. So actually quite cool. You can reuse all the theory from shared memory programming here. It's an equivalent model, I would say. And it's quite powerful. Okay, so this is kind of your global distributed RMA, remote memory access programming model. I would not want to say shared memory because that's a different definition. Yes?
So while we're talking about flashes,
yes.
OpenMP defines flushes had a lot of other synchronizations as well.
Yes.
Is the same true in the MPI part as well? So that the flushes imply a barrier, for example?
Correct. No, that specifically is not correct, but some things are implied. So we have a barrier as an MPI-1 operation. So barrier has absolutely no influence on the memory of a shared memory window. However, if you want a barrier with synchronization, then you do an MPI-win fence with a barrier, right? The unlock here, the unlock has flush semantics. So that's why I said exactly. So some of these operations have flush semantics. Every single time you close an epoch has flush semantics. So for example, if I'm issuing an MPI-win fence, all processes close an epoch and open an epoch, and that has the same semantics as if you do a flush at every process followed by a barrier. Right? It's exactly the same. In fact, most of the implementations are like this. So our implementation for MPI RMA is doing a flush and then a barrier, and then we call this fence. So there are some, but you have to be very, very careful. Collective operations of MPI-1, like the barrier or reduce or whatnot, they have no side effects whatsoever on Windows, right? Because these are two different worlds. You can mix them, but they don't influence each other. It's actually quite powerful, again, that you can mix them freely without having side effects. The big downside in OpenMP, for example, is that if you issue any operation, it has this very potentially heavyweight side effect of synchronizing everything. And these can be quite expensive if you look at microarchitecture implementations. So in MPI, you have the choice to do a barrier without synchronization of memory, which I find quite cool. But you have to be careful. It's a very good question, yes. So remember, everything that closes an epoch has flush semantics, and everything else does not. Right? Okay, cool. Any other questions? Very good. So now the memory model that I want to make very brief, because that's now really heavyweight. I just want to introduce the concept that MPI specifies. There are two concepts. That is the separate model and the unified model. The unified model. In MPI-2, they only had the separate model, which is why MPI-2 could not be implemented fast on cache-coherent architectures, because the separate model is for a system that is logically not cache-coherent. Right? Then we thought, well, you know, there are not too many of these kind. It basically was one at the time. I'm not even sure if it's still alive. Most systems today are cache-coherent. And we can talk about GPUs. In fact, GPUs are coherent with respect to the NIC. They are not coherent with respect to other SMs. So if you want to go into details, again, I can go into arbitrary details in these things, but I'm not sure if that's of general interest. Here in this MPI-3, we have this new unified model where you basically can say, well, you know, I know that my network card is, you can query it, you don't have to know it. You can ask the MPI library, does my network card support the unified model? And then you can use that model. What does that model mean? It means that all your accesses are much stronger. So to just give you a little bit of a conceptual overview, in the separate memory model, you have two different versions of your data. You have a private copy that you access with load store operations through your program, and you have a public copy that you access with remote memory access operations through the MPI library. Right? So that's the put and get accesses the public copy. The private copy is accessed by load and store of the CPU. And these are different. These are completely different views of your data. They may be completely different, which is extremely complicated to understand in practice. And then there is some synchronization between those guys. Okay? In the unified window, it's exactly what you would expect. The unified window, there's only one view of the data. If I read and write with the CPU, I get the same view of the data as if I read and write with a network card. Right? This is the nice model to program in. And this is basically supported by everything today. So you should be querying this at the beginning of your program and only use unified. And then we could now define what the conflicting operations are, but I want to spare you with this because that's too much. So, but you can basically see is in the separate model, there are lots of things that are just not defined or forbidden. In the unified model, these become suddenly nice for non-overlapping accesses. Okay, so very good. So now as a last thing, I want to briefly discuss this MPI and shared memory. So what does this mean? So you can actually use MPI for programming hybrid systems now in MPI-3. So what is a hybrid system? A hybrid system is a system that contains shared memory nodes together with distributed memory nodes, which is basically any system you have today, right? Because you have multi-core that has shared memory, and you have many nodes of these multi-core things that is then distributed memory, right? And the problem with that is that if you have large data, like these physics tables, for example, you don't want to replicate this at every node, at every MPI process, I'm sorry. You want to replicate this once in a shared memory domain, and with this you use MPI shared memory. So this nicely integrates with everything I just said about one-sided. I can cover this very fast because all you do is you create a special one-sided window that is then your shared memory. And then the semantics get very complicated, but I'm not going to talk about this. The reason is because, again, you only care about this if you're worried about all the corner cases, which nobody worries about in practice. Okay, wonderful. So what is this? And again, one most important thing is this control sharing. You can actually implement a program in a shared memory domain where you share only pieces of your program. I like this much more than OpenMP, again, because there you have shared everything by default. In MPI, you have controlled sharing where you have separate processes and a bug cannot overwrite your heap of the other process, which are the nastiest bugs that I've seen so far. If something overwrites your control, then you go really crazy. Or it's very hard to debug. Okay, so how does this work? Of course, as I mentioned, we have now multiple cores. These are cores here in different nodes. So we have 3 nodes, 1, 2, and 3. And we have 4 cores in each node. And if you have MPI world, that's of course including all 12 processes. In MPI world, you cannot tell which processes are on the same node. So, but of course, you need to tell which processes are on the same node because you need to figure out where your shared memory ends, right? This is why there is a specific function now that is called MPI split type. That is a function that splits the communicator into multiple smaller communicator with a specific type argument. There is only one type argument that is valid today, but maybe later comes a new one. That is type shared, which basically means if you split the communicator with split type and the type shared identifier, then it'll split it into this particular one into 3 shared memory communicator with the first 4 ranks, the next 4 ranks, and the next 4 ranks. So we have this communicator, and this communicator, right? So we get 3 out of it. Basically, a more formal definition of MPI split with type shared would say it splits it into the largest subsets that enable shared memory communication, right? So the smallest number of communicators that enable shared memory communication, okay? And then what you can do on these communicators, you can call win allocate shared, which basically creates shared memory windows. So you will have 3 shared memory windows, one here, and one here, right? And these will be shared across all processes on the same node, okay? And this magically figures it all out for you. So you don't need to figure out which processes are on the same node or not. And then it gets a bit more complicated, but actually still simple. So these shared memory windows, they now actually allow different processes to not just put get. You can actually put get into that window if you want, but hey, it's a shared memory window, which means you can just load store into that window. You can now, they all see the same thing. This process 0 and process 1 can issue load stores, and actually even to the remote region of that process, because in that window there is actually no remote region. If you want, you can create a remote region. You can create partitioned versions of these. But by default, there is no remote. By default, it's again the OpenMP mode where it's just memory. It's not clear which process it belongs to. Okay, so you can use all the existing RMA functions if you want, but you can also use load store. And this gets quite confusing in details, but again, only in details. Because what do you now do if you do remote store and then remote puts over that thing, and what is the epoch exactly? But that can all be worked out. But what I would recommend for these operations, you just use load store. You use shared memory as if you use shared memory. Yes?
Is this all shared by default, or do they have also private memory?
So only the memory that is in the shared memory window is shared. Right? So this is this controlled sharing. They have all private memory by default, but only that one array or that one data structure that you expose can be accessed as shared memory. So we will go through a code example, but let me first introduce the functions. So here's this split type thing. that basically splits this communicator COM with the split type. And again, there's only one split type, which was this, and I forgot exactly, this COM shared thing. This is the key, the usual key that you can use for split type applies here as well for the rank assignment. So basically you can renumber the ranks if you wanted to. MPI info, let's just forget about it, and you get back a new communicator, right? So once you have done this, you can call this MPI win allocate shared now on this resulting communicator, okay? So you specify a size, you specify again your displacement unit because there's an MPI window at the end, but you can ignore that displacement unit if you use shared memory accesses. You have this MPI window as usual. You have a base pointer because that's the pointer you get back. This case, it has to be allocate. There is no create function. It must allocate the memory for you because it must allocate it as shared, right? And then you get back a window. So how does this look in the real code? So you have in main, we have MPI init, MPI com split type with this type shared, MPI allocate shared with this window. Then we issue a lock all just to make sure that all the memory is consistent. And then we can copy data. And now there is an interesting function, MPI win sync, which is now the equivalent of OpenMP flush. Right? Because you still need to worry about the memory model of your local CPU. Right? So now you have an MPI memory model, but since you now have shared memory, you have an interaction between the MPI memory model and the rather complex memory model of your local CPU. So in x86, it's simple because it's TSO. You're only missing one order, 1 out of the 4. But if you run this on an ARM architecture, it's going to be crazy because they have a very relaxed memory model, at least as of today. They want to strengthen it. So this is why you have to use these synchronization operations basically after every write to that window, you just synchronize, and then you're safe. Right? You can try to make this faster again, but I would not experiment too much with memory models. It's getting extremely complicated very quickly. So just use, you write data, you do a sync, and then you can use this shared memory, and then you do an unlock all at the end. But you don't even need this lock and unlock unless you use MPI operations on that window. And then you do a free and finalize. Okay, wonderful. So now it gets a bit more involved if we wanted to talk about this. So I'm not sure. So we are already over 5 minutes over the break. So who is really interested in how to place memory in these windows? So there's also a way to exploit NUMA capabilities with these windows, but this is quite an advanced topic that I could cover in about 10-15 minutes. Then we would only have 10 minutes break left, but we could also skip this now and take the full break in case you have questions for me, because right after the next session, I have to run to a train. So there will be no questions after the next session. So let's have a vote. Who wants me to talk about this for 15 minutes? Okay, everybody else wants a break. Very good. So let's take a break. Okay, so now we have 2 more things that I wanted to talk about. One is advanced MPI. So this is something that's really at the very close to my heart because it's something that I've been working on most of my PhD and postdoc time. And if you've heard about my past, it was basically non-blocking collectives was my starter in MPI, and then RMA came kind of later in a bigger group. Okay, so I will be talking for about 30 minutes about non-blocking collectives. A couple of cool insights that may not be so clear because I see a pretty advanced audience, so that's actually quite exciting. And then at the end, I will give another piece of advice that Paolo asked me to give, essentially how to benchmark correctly on parallel systems, which is mostly an entertaining talk that shows how to not do things, but also provides insights how to do things correctly. So, but it's mostly meant for entertainment, so a light ending, I hope. Okay, very good. So non-blocking collective communication. So who of you knows non-blocking send-receive communication? Oh, not so many. Okay, so who? Interesting. So you programmed MPI without non-blocking. So then let me explain this a little bit, but I don't have too much time. But non-blocking send-receive communication is a very, very simple concept in the sense that you can, when you issue an MPI send or an MPI receive, the control or the function call will only return once the send or the receive is logically complete. It's very important to say logically complete because it doesn't mean when you issue an MPI send that the message, and it returns that the message actually arrived at the destination. It just means that you can reuse the buffer that you specified in MPI send. That's all it means. It's like a logical completion. It's not a physical completion at the destination. So why do you care about non-blocking then? So non-blocking is a very similar idea. Well, you issue an MPI send. However, you want the function to immediately return irrespective of the completion. So the function returns. And now the problem is, how do you ever check for completion? Well, the function gives you a handle that's called an MPI request, right? That you can later investigate whether that the function call associated with that request has completed or not, right? That's the important thing to remember. So blocking communication means I just issue the operation, and whenever the operation is logically complete, it'll return. Non-blocking communication means I issue the operation, and the function returns immediately and gives you a request that you can later check whether that operation actually completes or not. Remember, or note that I see function and operation as separately. Function is just a call you call, which may or may not, which completes independently of the operation. The operation is the actual thing that the call does, like the send or the receive itself. Right? These are two different concepts. But this is more like the basic MPI course. So non-blocking communication, why is that needed? Well, that is in fact necessary to make this stencil example that I showed before deadlock-free. Because somehow, in the stencil, as you can imagine, okay, let me not draw it because you probably know it. If I have 4 processes, right, there is now a circle among these 4 processes of send-receive dependencies. Right? If you look at the process 1 sends to process 2 sends to process 3 sends to process 4, and process 4 also sends to process 1. Right? There's a very large number of circles in there. The problem is now, if the send or receive turns out to be blocking, then you have a deadlock. Right? So then your code cannot complete. The solution in MPI-1 to this problem is, well, you just make all of these calls non-blocking. You just say, well, I'm issuing MPI, they're called I-sends. And the I, by the way, stands for immediate return. The I is immediate and the return is implicit. It took me the longest time to find this out. I was always wondering why it's not called MPI asend for MPI asynchronous send, because it is not asynchronous. That's the thing. Isend just means the function is returning immediately. It doesn't mean that there is any asynchronous operation going on. Okay? It is really just standardized for deadlock avoidance. Because if I now do isend, I receive, there is no circle. Because now the MPI library is free to find a valid ordering for the messages. While before, you force the MPI library to do your ordering of the messages. Because you do first send, and then the second send, and then the third send, and the MPI library has no choice but completing them in order. You give it no choice. In the non-blocking way, you give it choice. Right? This is what this deadlock avoidance is. A secondary use of non-blocking operations, and it's really a secondary use, is to overlap computation and communication. Because now what you could say is like, oh, nice, I can start my communication operation with the I send, and then magically the communication operation happens while my node is computing something else that is independent of the communication. Right? This is overlapping of computation and communication. It can be extremely frustrating to do this, and I'm speaking from experience. Because many MPI implementations just choose to not do anything magically while you do your computation, and then you will basically issue an MPI wait at the end, and you will do the whole communication in the wait. And then you haven't gained anything. In fact, you have just introduced additional overhead for managing the MPI request, so your code is slower than before. Right? This is actually a big part of my PhD thesis I spent on this. Not so simple. Actually, not so simple because the underlying architectures do not quite support this. The nice thing is that MPI RMA that we talked about in the last session is really well supported by the underlying architectures. So if you want overlap of computation and communication, you use RMA, if the implementation is nice. Because there, everything will just be offloaded to the network and will magically succeed. For non-blocking send-receive, it's a gamble. It may or may not work. It's quite complicated. I could talk about this for an hour. really, if you're interested in this, let me know afterwards. This is quite a complex topic, but I'm assuming you know this. So who knows about collective communication? Okay, so really that little, okay, come on. Okay, so then let me also briefly explain collective communication. Interestingly, so everybody used MPI, so n-1 people used MPI, but most people, okay, these are the basic concepts in MPI-1. So collective communication is also something relatively, a very simple concept in MPI-1. So the idea here is that I have a function call that does some kind of collective data movement, collective operation, computation or synchronization. So there are three kinds of operations in collectives. You call them on the whole communicator at the logically same time, same as the MPI-Win fence or as the memory allocation routines or memory exposure routines in MPI-RMA. And they perform some data transformation collectively. Well, unless it's a barrier. A barrier doesn't do any data. So there are operations like MPI broadcast, for example, where a single node, a single MPI rank has a piece of data, and after the operations, all MPI ranks have that same piece of data. Right? It's a very simple replication operation. There are reduce operations where every node or every MPI rank has a number, and after the operation, a binary operation, after the collective operation, a binary operation of all the numbers is returned to one or all processes, depending it's a reduce or all reduce. So there are 17 of these operations that perform various data transformations. Okay, these are collective operations. They're extremely powerful. If you're an MPI programmer, you should be using them. You should be thinking 15 times before you do anything that looks like all processes perform a single operation together, not with a collective. Okay? So in fact, you should be thinking 20 times, because many people think they can implement this better in point-to-point with send-receive, but that's not the case most of the time. Okay, cool. So now what did not exist in MPI-2 is a combination of the two. So take the non-blocking and the collective together, and this is quite conceptually a very simple thing. We call this non-blocking collectives, and we just take the goodies, put them together, and now we have collective operations that work in a non-blocking way. Okay, so they're obviously good for one thing, that is this communication-computation overlap, but I mentioned that's complicated. Okay, so maybe it's not so good for that case, but it really depends on your architecture. It is quite nice if your system is imbalanced or if you have system noise. So what is system noise? System noise is basically if you're running on a very large scale system. So by very large scale, I mean at least 10,000 processes. So if you get into the millions or 100,000s of processes, it's very likely that you hit this. So it will be the case that one node, for whatever reason, runs a little bit slower than the other node. One very likely reason is that you have self-correcting memory, for example, right? ECC memory. So an ECC memory means that when I'm reading a piece of data, I may make a mistake with a very low probability, like 10 to the minus 19 or something like this. Actually, but there may be this mistake. And if this mistake happens, the memory will correct itself by applying a checksum and rereading the value and then correcting it. But the problem is this takes longer than a single memory access. So what this will basically mean, there will be at one process with a very low probability, there will be a delay for this correcting purpose. By the way, if you don't have ECC memory, you will just read the wrong value, right? So that's not better. Then your computation will just be disturbed in some way. But if you have this kind of memory, there will be well, tens of microseconds delay at this one process. The problem is now if you have 1 million processes and one of them with a very high probability is now delayed every couple of milliseconds for tens of microseconds. Because 10 to the minus 19, you take 1 million, immediately 10 to the 6 less, so 10 to the minus 13. So now look at a reasonable time and you will see with a high probability you will see this at a very large run. Okay? And this is what we call system noise. So basically some nodes run slower than other nodes for various reasons. And the problem is now, if you have 1 million nodes, one runs slower, 999,999 will wait for that one process in the next collective operation. Right? Because the collective operation only completes when all processes have done something, at least most of them. Right? All reduce, for example. And so this is a problem. At Google, this is called the effect of the long tail, by the way. So they kind of rediscovered that effect in the data center environment. It's very, very relevant for data center environments as well. Okay, So you can use these non-blocking collectives to hide that effect. The way you hide it is you basically take you introduce a buffer from the initiation of the operation, the non-blocking call to start the operation, to the completion of the operation, which gives a buffer for these small perturbations at various processes, right? So that's the idea. Okay, cool. But now let's look a little bit more at the semantics. How does this look like? Well, we have non-blocking variants of every single collective. It is extremely simple. We just take the normal collective, like a broadcast in this case. We add an I at the beginning. Then it's the immediately returning broadcast. And we take the normal arguments of that operation, and we add an MPI request at the end. Trivial. Okay, good. So syntactically, that is no problem at all. So you can easily fix this. So what are the semantics now? Semantics are that this function, this I function, returns no matter what. A normal collective call will actually only return, in many cases, once the other processes have called that call. Here, this I thing will return no matter what happens, pretty much immediately. Furthermore, there is no guaranteed progress, so you cannot expect that anything happens magically in the background, same as for non-blocking point-to-point, right? So there is no difference here. Then you can use the usual completion calls, wait and test, with that request, right? So I'm assuming you know this from non-blocking point-to-point. It's really easy. A wait call just waits until the operation completes. A test call just tells you whether the operation completed or not and does not wait for anything. Well, okay? And we have out-of-order completion, which is also quite funny. If I'm issuing MPI-I broadcast and MPI-I gather, it may be that the MPI-I gather completes before the MPI-I broadcast. So you cannot rely on the MPI-I gather completing, implying that the MPI-I broadcast completed. So they may complete in any order depending on what's faster.
Professor, what do you mean by mixing?
So you can actually, there are completion calls like wait all, wait some, wait any, test all, test some, test any. And you can mix requests from non-blocking point-to-point, from generalized requests, from non-blocking collective requests. You can mix them all into one wait some or wait any. This is what I mean. It's a perfectly valid MPI request, basically. There's no difference. Now there come some restrictions for these operations which are quite funny. They have no tags. Because non-blocking point-to-point has tags. Right? So you can differentiate different messages. Here you cannot. And some people complain about this because they say, well, you know, I have these different collectives and I want them to match differently. This is quite an advanced use case. If you think you need tags for collectives, really only if you're sure, and that's the name, if you're sure you need tags for collectives, there are use cases for this, very rarely. You can use communicators as tags. That's the trick. If you need 5 tags, you do 5 times MPI comdup, and you use the communicators as tags. You shouldn't be doing this without thinking about it, because 5 communicators are quite expensive. Actually, they're not so expensive, but on some systems, they're ridiculously expensive, but they should be really cheap. It's an implementation problem if they're expensive, but unfortunately, some systems have that implementation problem. So remember, no tags. If you absolutely need them, you can use communicators. What's obvious is that these send and vector buffers, they should not be updated during the operation, the same as for MPI-I send, because like, what happens if you update it? It's currently communicating. We do not support MPI cancel, right? Just because it is too complicated to support. Because collective operations involve a whole series of messages. It's a total mess to cancel this. It's even MPI cancel, if you know the semantics, it may even fail for blocking point-to-point or for non-blocking point-to-point because it is too complicated to cancel in some situations. So we just decided to not support it. We also do not support matching with blocking collectives, which is also not a problem, but you need to know. So for example, in non-blocking point-to-point, you can have an I send that sends a message to a receive, to a blocking receive. You have a non-blocking send to match with a blocking receive. That's totally normal. Or vice versa, a blocking send with a non-blocking receive. We cannot do this in non-blocking collectives. We cannot match an I barrier with a barrier. You will deadlock. Sorry, it will not happen. Or you may deadlock, you don't have to. The reason for this is very simple, because non-blocking collectives use different protocols than blocking collectives for the implementation. So they cannot be matched. If you need this, it's totally trivial to do this, because you know what a blocking collective in terms of a non-blocking collective is. It's the I collective immediately followed by a wait. So if you need this, it's totally trivial to implement. Okay, so what are the semantic advantages? I already mentioned this. We have asynchronous we have potentially asynchronous progression, depends on the quality of your implementation, right? Many today are moving quickly into the area to support it. It's a major research topic. Some systems, actually like the Cray systems, the modern ones, they support asynchronous progress for non-blocking collectives with some environment variables. MPITch as well, by the way. They decouple data transfer and synchronization. I already mentioned this at the beginning, at the introduction. And they allow overlapping communicators, which is also quite funny. However, if you think you need overlapping communicators, you should be looking at neighborhood collectives, and I don't have the time today to talk about those. But this is also a very interesting concept. It's basically if you have, so neighborhood collectives is the Lego building blocks of collective operations. So just to give you a short overview. So if you have a collective pattern that is not supported by one of these 17 calls in MPI, like for example, the nearest neighbor exchange in the stencil program I told you before, that is not supported by a collective call to exchange it with your neighbors. However, neighborhood collectives allow you to build your own collective. And it's quite cool. So in a data flow manner, you specify what are your communication relationships, and then the MPI library will compile this into a communication schedule for you. You don't see this. And then you can just start that communication later. It's quite a cool set of building blocks. Again, I unfortunately don't have time to look at this today. And then we can have multiple outstanding collectives at the same time, which is quite nice. So I can actually pipeline collectives. So I can say, well, you know, start broadcast 1, start broadcast 2, start broadcast 3, and they run at the same time, kind of. Okay, so again, it's a performance thing. Okay, so I actually think that all of you understand non-blocking collectives now. Yes?
Can MPI or build an MPI implementation basically pack all these outstanding packages together? If I do multiple I broadcasts on same data, pack them together and basically then all the data together to everyone else and then unpack them?
It could. It could, but it most likely doesn't. Because it's a library, remember. When you issue the first I broadcast, it doesn't know that a second one is coming. So it would first need...
If all the progress is done in the MPI way.
Yeah. It would first need to delay the first one, right? Not immediately start it. And then see whether another is coming. So, which is the case if all the progress is done at the end. Then it could totally pack them all into one. I don't know of any implementation doing this, but it would be a valid behavior to do this, yes. So it could be an optimization, so next Euro MPI paper. Yeah, that sounds like a good idea. But actually, one of the things here that is not so obvious, at least it was not obvious for me for nearly a full year. So I actually pushed this optimization, so the standardization of non-blocking collectives, and then every time in the forum there was somebody cracking a joke, is like, yeah, what's a non-blocking barrier good for? That is totally useless, isn't it? And if you think about it, what is a barrier good for, right? A barrier is semantic. It doesn't communicate any data. It basically just waits, like all processes that call a barrier collectively wait until the last process arrived to call the barrier. So what freaking value can it then have that a non-blocking barrier immediately returns and doesn't wait? So that doesn't make any sense because it doesn't seem to make any sense because the semantic of the barrier is defined in terms of waiting, but now it doesn't wait anymore. And now you could say, well, okay, we can decouple synchronization from itself somehow, and we could overlap barrier latency here, for example, because they could all call iBarrier and then later, once the barrier finished, do the wait. Barriers are so fast, that doesn't make any sense. That was my first hope. It doesn't work. However, there is an incredible, non-obvious use case that we came up with. Actually, in a discussion with Rolf Rabenseifner, we came up with this, and Christian Siebert. So it's a quite interesting use case that I want to explain to you, because that is a very non-obvious way to use these split semantics. What are the split semantics? The split semantics are basically that I have now a collective operation that consists of two function calls. The initiating function call of that operation is non-collective, which is really weird. Right? So you kind of, it's non-synchronizing. It is still collective, but it's non-synchronizing. So which means it returns no matter of the state of the other operations. So basically I can say here I reached my barrier, and then I can go and do something else. Right? In a normal barrier call, I would say here I reached my barrier, and I would need to stand here with my hand raised and cannot do anything else because I'm waiting until everybody reached the barrier. Right? This is the basic difference. So we have this split semantics between saying that I reached the barrier and do something else and help somebody else versus saying I reached the barrier and I can't do anything, can't help anybody. Right? That's what I call split semantics. And then later, of course, you need to call the test or the way to figure out whether it completed. So let me now give you a use case for this. So the use case is very ubiquitous, in fact. The abstract name that we gave it is called dynamic sparse data exchange. So it captures two main terms, dynamic and sparse. Data exchange is obvious. So dynamic means that the communication topology, like the neighborhood relationships between senders and receivers, are rapidly changing. Okay? So it's not the same all the time. Because if it was the same all the time, like in the stencil example, I would just build a neighborhood collective. And I would do that over and over and over and over again. Right? However, if that is changing each iteration, it is way too expensive to build a neighborhood collective, right? Because that takes us time to set up. Sparse means that this pattern that I'm communicating is not an all-to-all like pattern. So I'm only communicating with some selected neighbors. In fact, in computer science theory terms, I would say it's an O of log p number of neighbors. Well, p is the number of processes in my communicator. So I need kind of an exponential gap. I need a very sparse communication pattern. So here is this O of log p. So the number of neighbors is limited. And data exchange, the idea is that in this case, only the sender knows where to send the data to. And we will see a use case for this. Oh, I can explain you a use case right now. The standard use case for this, only the sender needs where to send the data to, is a particle code. Right? Imagine you have a particle code where you decompose the domain of particles to 4 processes. Okay, process 0, 1, 2, and 3. And each process holds a piece of the real world particle domain and has some particles in it. So then you compute your forces, and then after you computed your forces, you do advection, right? Because you want to move the particles. The problem is now, of course, that if one process moves a particle into another process's domain, it may happen because it may be at the boundary to the other process, only the source process knows that it actually moves that particle to the target process. The target process has no clue that there is a particle coming. Right? Does that make sense to everybody? So it's really, and this is basically in any irregular program in parallel computing, that is the case, because the source owns the thing and may need to pass it to some other process, but that other process doesn't know about his or her luck to receive the thing. So this is what I mean, the only senders know the neighbors. So if you now generalize this, you may actually have a problem where you may be talking to every other process, but this other process does not know that you have data for that other process. Right? And this is this communication pattern. So the main problem in this communication pattern is basically the figuring out who wants to send how much data to me. Because in MPI, what I need to do is I need to post the receives. Right? Or I use one-sided. But even in one-sided, I need to allocate memory to put the data into and tell the source to put that data into that memory. Because otherwise, where would it put it? Right? It has to figure out the memory allocation. So,
Torsten, if I may interrupt.
Yes.
So the molecular dynamics guys or the finite element guys might think that in any case, those neighbors are always the same.
Well, then you use neighborhood collectives.
Exactly, but that's there are use cases where, because of the physics that happens, so the particles are thrown away out beyond the closest neighbors.
Exactly.
So yes.
Exactly. So if you always have the same neighborhood, don't use this. But there are very strong, usually in the particle domain, so where particles can move at varying speeds, and your domains are small enough that you can cross multiple neighbors. In fact, that is necessary if you scale very far. Right? So if you need a lot of domains. If your domains are very large, that you can only reach so far into the neighboring domain, and you know that you will never fall out of that, then it's again relatively simple. But as Paolo mentions, yes, there are these use cases at very large scale again. So now you need to figure out who sends, or actually what you can also do if you're an MPI-1 expert, if you just know how many messages you're receiving, then you can actually use unknown sender and unknown message size receiving. Right? You just post a message with any source and any tag, and then you use MPI probe to figure out how big it is, and then you receive it. Right? So basically the the problem can be reduced to counting the number of neighbors. You could now also say, well, potentially, I'm receiving from all processes in the system. So I will just post p minus 1. If there are p processes, I will post p minus 1, and they will send 0 size messages. That is very inefficient, right? If it's sparse, because then I will have an exponentially higher number of messages than I need to, asymptotically. So just to illustrate this a bit more, so if you have process 0 here, for example, that has a message of size 1 for process 1, and a message of a message of size 2 for process 2. Process 1 has a message of size 3 for process 0, and so on, right? Here, process 2 receives from two sources, 0 and 3, but it doesn't know, because only 3 and 0 know that they send to process 2, okay? So can anybody tell me an idea how to implement this? I just told you one, right? You could post n minus 1 messages and then probe receive them, but that is O of n overhead. Yes? But how would you do this? Because you would still need to write for every single process, even if there is a 0, you would need to write to it, right? So you again have O of n overhead, essentially.
Not necessarily, so if you initialize the array with 0 on each flank.
But how do you know that they're done? How do you know?
Fence.
You have a fence. Aha, okay, good.
So you have to synchronize.
Yes. Okay, so you could do this, right? You could initialize an array of 0. You could write in the non-zero elements with O of log n operations, and then you could do a fence of O of log n. So we just invented an O of log n protocol. Very good. Takes 2 steps, though. We can get rid of 1 step. Any other idea? The way this is implemented on any code that needs this is an all-to-all. It's really bad. But this is what people implement. Brute force, yes. So you could do an all-to-all where you just fill in the numbers, right? So we're basically saying process 0 sends nothing to 0, size 1 to 1, 2 to 2, and nothing to the other ones, and so on. The all-to-all will just transpose that array, and then everybody knows what to receive. That is an O of n algorithm, O of n square messages, very bad idea, right? So you just invented a better one. And just saying. There is another one. It's quite interesting. This is one of the rare use cases for reduced scatter. So who has heard about the reduced scatter function? Who has used it before? Oh, so somebody used it. Because that was one of the things that I was never clear what to use it for. For matrix multiplication, you could use it, but it gets you a very inefficient algorithm, so it's not so great. In this case, what you could do is you just initialize, again, like in the previous case, exactly the same. But instead of saying the message size, you just say I'm sending 1 message to process 1, 1 to process 2. The size does not matter here. And then the reduced scatter, what it'll do, it'll sum up the row, the first row, and send it to process 0. And this should actually be a 1. Okay, sorry, this is incorrect. So this should be a 1 here. The second one is a 2 that matches. The third one, okay, this should also be a 2. This is basically the number of neighbors you will get. So sorry for that slide, I need to fix this. I thought I had it fixed, but yeah. And then what you do is you just receive that many messages, right? Once you have run that protocol, process, let's say process 2 knows it needs to receive from 2 processes. It doesn't know which ones, but it just posts 2 receives, and once these receives are satisfied, it knows it's done. Okay, very simple. Now let me tell you how to do this with an I barrier, which is a slightly more advanced protocol. That's actually kind of the coolest part of this lecture. So pay attention for a couple of minutes. This is a protocol that is using basically the consensus of the non-blocking barrier in a non-intuitive way to solve that exact problem. Okay? It uses another function that is called MPI-IS send. Who knows what an MPI-IS send does? Yes?
Yeah, synchronous send. That means that the data transfer is complete and not just buffer.
You're right for all practical purposes. In MPI specification lingo, we would say that the message has been matched at the target. It's not, the data transfer isn't complete, but the data transfer will complete. That's what you could say. Yes, but for practical purposes, you could also say it is complete. There is semantically very little difference. Very good. So, but it's a non-blocking version of the S-send. So what you do in this protocol is all the processes, they don't have two stages, like the metadata and then the real stage. They just do this in one stage. They basically all start IS sending their data. So this guy IS sends this message to 2. This guy IS sends this message to 1, and so on. They just IS send everything, right? And then they go into a loop. And the loop is now an iProbe loop. Of course, because like once we send these messages, we have to receive these messages. But we don't issue a probe because a probe is blocking. We issue a non-blocking probe, which basically checks whether there is something to receive. I go into this loop and say, is there something to receive from me? If there is something to receive, I'm just receiving it. But remember, I don't know when to stop receiving. That's the problem, right? Because I don't know how many messages I will receive. I may get 15, 20. I just know an upper bound, which is a number of processes, but that may be too many to receive from. So what I now know, I know with this IS send, when my local messages that I send to the other processes have been completed at these processes. And that's nice, right? So that's some knowledge. So I basically know when I am done sending, right, as you just mentioned, right? So when I'm done sending, I just say, hey, I'm done in a barrier call. Okay? However, the problem is I may still need to receive. So I cannot issue a blocking barrier, because if I issue a blocking barrier, then I cannot receive anymore. So what I do is I issue a non-blocking barrier, but keep receiving in this iProbe loop. So when can I stop receiving? I can stop receiving once I know that everybody's messages have been received. Because then by implication, I have received all my messages like everybody else. And this happens when the I barrier completes. So I'm basically going into this loop, constantly test, is this barrier complete, is this barrier complete? But I have to keep serving the receives for the other processes that I don't know. Right? So this is what I mean by kind of a non-obvious protocol. You can generalize this protocol. People have been using this for all reductions, because in an all reduce it's very much the same, besides that you have the side effect of a sum at the end. But this is how to mix blocking sends and receives, no, actually not like non-blocking synchronous sends and receives with a non-blocking barrier. Okay, is that protocol kind of clear to everybody? So that's kind of the coolest. It's non-obvious. It usually takes a while to understand. Okay, very good. So this is the way to use it. You can now implement certain things with it. And if you don't understand it, there is a research paper on this, which is from 2012. Hmm? It's very hard to say, because it really now depends on all kinds of details. How good is your RMA implementation? How good is your collective implementation? I will tell you on one system, this is the fastest you can imagine. That's the Blue Gene system. Because the Blue Gene system has a hardware barrier. Yeah. So if you have a hardware barrier, so a Blue Gene system basically is a system that can synchronize the whole machine in a microsecond. Right? The whole machine meaning 100,000 processes in a microsecond. It's quite nice because they have a specialized network that is a 1-bit network that just has a pull-down transistor. It's just everybody who's done pulls down the transistor, and the others just measure the voltage on the thing. Right? So it's a very nice, okay, that's abstract. There's a little bit more to it. But it's a very nice hardware implementation of this 1-bit information, I'm finished. Right? So in that system, this is unbeatable. As you can see here, basically you're down here, right? So this is the Blue Gene with a hardware barrier implementation of a graph algorithm that uses that protocol, and this is the all-to-all protocol. Oh no, this is the reduced scatter protocol. The all-to-all protocol was way too slow. This is another protocol which you didn't come up with. Actually, usually, I like your protocol you came up with, by the way, but usually people say you could use an accumulate to count the number of neighbors you receive from. Right? So that's also kind of an obvious way to do it. You could just accumulate into one buffer instead of this array. So you have O of 1 memory overhead and not O of n memory overhead. And then you do a fence at the end. Right? This is this PCX protocol. But defense at the end will still need some time, and the hardware barrier will just beat everybody hands down. By the way, there are more architectures coming up with hardware barriers because they're quite nice for machine learning, and since that's where the money is, yeah, that's where hardware barriers will come back. If you don't have a hardware barrier, it's still the fastest on this old network, but again, it depends on all kinds of, I don't want to over-advertise this, it really depends on on the system architecture and all kinds of things, what faster even means. Okay, so that for the non-blocking collectives, they have very, very simple semantics. I just presented you one non-trivial example of how to actually use these semantics in a non-trivial algorithm, and now you should go and dream about how to use this collective invocation without synchronization and the later non-collective synchronization of the collective operation, right? Which is quite funny because it's exactly like I said. It's non-simple to understand. So with that, I would like to get to the last part of this lecture, and that's now kind of the fun part. At least for me, we'll see how it is for you. So this is the talk I really like giving. It's how to benchmark systems correctly. Because there is a lot of confusion in the field. And actually, what is most important for you as scientists, I'm assuming all of you are somewhat aspiring scientists in one way or another, is that you want to make sure, and you can read this on the side if you like, that you want to make sure that whatever science you produce, whatever scientific results you produce, are actually reproducible to some extent. This talk will motivate why reproducibility is, in my view, impossible for performance-related arguments, because the reason is the result I showed you just 5 minutes ago on the blue gene machine, none of you will be able to reproduce, because there is no blue gene machine anymore. Right? So this is a bit of a problem for the community. So in this sense, computer science and HPC is not like the traditional sciences where I could easily, or not, well, with some effort, build a machinery to reproduce experiments easily. Somehow for us, on large-scale systems, it may actually be in the realm of impossible, or physically or financially impossible of reproducing a result. So this is why we need to follow in benchmarking, in the case of benchmarking systems, some guidelines that enable at least to interpret the results, that they don't lose their value later. Because the scientific principle bases on reproducibility. And if we don't have this, then we have a problem. And actually, my point is we have a problem already now in the community that we need to address in many ways. So again, but this is kind of supposed to be funny. So I will make fun, mostly hopefully of myself, but also sometimes of other people, and I will criticize things. It's all anonymous. However, if you see yourself, then please smile and be happy. So it's we will see. By the way, this whole reproducibility is a quite complex field because there are two different terms, reproducibility and replicability. And there's actually confusion about these terms between the ACM and the physics world. So the ACM has the inverse definition of the physics world. I never understood why. I'm going by this definition here. The reproducibility is the ability to recompute results. So basically take the exact experimental setting and repeat it. The replicability is that experimenters in another experimental setting, so the reproducibility is I download the code and I do the same thing that the original people did. Replicability is I'm trying to replicate the effect by writing my own code in my own environment and see whether that helps me. So when you follow any of the guidelines I gave you for writing fast MPI programs, you're trying to replicate my work because you're not downloading my experimental setting. Right? So replicability is actually slightly more important than reproducibility in my view. But now the problem is this is, of course, that if you just download my code, you will get my code including all my bugs. So that may not be too valuable for you as a scientist. Because you may just, I don't know, download my complex physics package, and my complex physics package is fundamentally broken, but it's broken in such a subtle way that it's not easy to see. Right? And this is a bit of the problem. Okay, so now there's an interesting study actually in the Nature Journal 2016 where they asked a bunch of scientists whether there is a reproducibility crisis in the community. And they asked scientists across all disciplines, which is quite funny. So they asked the 1,500 researchers, and 52% said it's a significant crisis, and 7% they don't even know. But everybody else kind of agrees there is somewhat of a problem. And interestingly, they cut this into 3 pieces. So they asked the scientists, how much published work in your field is reproducible? Okay? And then they say basically 0% to 100%. The chemists are very sure, yes, it's all reproducible. The physicists are very sure, yes, it's all reproducible. The others, which includes computer scientists, they're less sure. They're like, it may or may not be reproducible. We don't know. Interestingly, if you now ask the same people the following question, have you failed to reproduce an experiment? Like the chemists have most failed to reproduce their own and other experiments, yet they are most sure that their field is reproducible. So there is some kind of interesting thing going on. And the others, actually, they fail least. However, they are also least sure. So there's kind of an interesting effect here in the perception of reproducibility across different fields, I would say. So as usual, computer scientists are very strict to each other when it comes to criticizing. We are extremely good at criticizing each other's work and not liking each other's work. Okay, so it's not so obvious what this actually means and what the state of the field is, but in general, we should be worrying about this. So if you worry about reproducibility of your scientific results, there is a good solution. You can actually use Docker or Jupyter Notebook, which you probably know, and if you don't know it, you should look into this. This is for the effect reproducibility. So get the same result with the same setting. It's a wonderful thing. The problem is now, if you do this for parallel codes, it gets more complicated. Because interestingly, for whatever reason, IEEE is not associative. IEEE 754, which is the floating point specification, is not associative, which means if I'm parallelizing a code, I may get different results depending on the number of processes I use and whatever. Right? So actually, if you care about real reproducibility, then you can achieve bitwise reproducibility. We have a paper on this quite cheaply. This is not even expensive. So this is for some operations an overhead of about 50%. But there's a very limited number of operations. So if you really want exact reproducibility, then you should look at this. It's not part of this talk. I just want to tell you that you can do it. And actually, it's a quite neat way to make floating point numbers reproducible. So again, I don't have time to talk about this, but this is a method developed by a fellow called Rump and made famous by Demel and Nguyen in an earlier paper. Okay, but again, I don't want to spend too much time about this. But now the question is, what if you really worry about performance? Not about the result of your code, but you are a scientist like me who talks about how fast is my code running, right? And it's very likely that many of you will actually publish performance numbers for your code, saying, look, I optimized my code and it's now running, I don't know, 10% faster than this other code. This is what I want to discuss in the remaining about 30, 45 minutes, how to do this. So I want to start with a story for myself, because it's always best to make fun of yourself. So I published a paper in 2006. It was one of my first papers on non-blocking collectives, as you can tell, so it's more than 10 years old. And what I did is I took a conjugate gradient solver and optimized it for non-blocking collectives. So I was always worried about reproducibility, so what I did is I put that code on my webpage. It's still on my webpage, okay? So what we found in that paper is, actually, here's a plot from this paper. This plot is the worst plot you can imagine. I would not do that. I would not allow any of my students to publish a plot like this today, but at that time, unfortunately, I did. So what the findings are, we can make this faster. So here it's a little bit faster. On an 800 cube domain, which is a 4 gigabyte distributed array across many, many nodes, right, with one process per node, on this Opteron 246, which at that time was already an old CPU, and today it's long dead, we achieved that speed up. Okay, so interestingly, we got a superlinear speed up for 96 nodes. Does anybody explain that superlinear speed up at 96 nodes? So superlinear means we get more speed up than we invest computational resources. So we get 96 nodes. Here you see, we get 96 nodes, but we get more than 100 speed up. How is that possible? Well, Paolo acts as if he's taught this, and now we'll see if any of his students. It's a cache effect, exactly. So as we scale, it's a strong scaling problem because it's an 800 cube domain, right? As we scale the problem to a larger problem size, it is more likely that it fits in cache because the domain per node gets smaller and smaller, and it happened that at 96 nodes, the whole thing fit in cache. Okay, that was one result. Then 9 years later, there came a science group that actually tried to reproduce our result, which is great. And they published a paper at a workshop on reproducibility, basically saying, oh, these guys are full of, no, they don't, their stuff is not reproducible. So, okay, interesting. So you look at this plot, and you find that they have two systems, this quad-core node system and then a dual opt-out system, and then they say, well, neither experiment in A nor in B could reproduce the results. So basically, we took our code, compiled it on the machine, ran it on the machine. So they could not see the superlinear speed up, blah, 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 as being a cache effect. So does anybody have a clue why they did not observe the superlinear speed up on a system 10 years older nearly? Huh?
No, it's less cache. Fills in cache already earlier.
Yeah, because 10 years later, the caches of the systems are much larger, much larger. So essentially, that system is that original 800 cube domain is way too small for that large system, or for that novel system. So it fits in cache from the very beginning, so you don't get the superlinear speed up. And so this is just one example that shows that even people who care really about reproducibility actually have trouble reproducing results correctly.
And this is weird, they already say it's explained as cache effects, so they should have looked at the caches.
Yes,
Weird
yeah.
work.
So reducing, this is just one example that reproducing performance is extremely hard. So this is one of the problems that I'm actually facing on a daily basis, that you cannot reproduce performance reasonably.
Torsten, before you move on, if you go back, you said that the top is the worst. There is actually worse than that. If you show timing, that's even worse than showing speed up.
It depends. I tend to agree and disagree at the same time. So we will see. Let's talk at the end. Okay. So actually, I did this own replication. So I just want to make sure that you understand that reproducing is worth something. So in this paper, we actually reproduced work by other people. So we replicated an effect and we replicated another effect, and we got a best paper award at SC for this. Right? So people are so surprised that you actually reproduce work that you get really rewarded for this sometimes. So please make sure that if you compare to other people's work, that you do this in a stringent way. And this is what I want to explain to you in the next couple of minutes. So again, reproducibility and replicability, what I would say is that for performance, reproducibility is extremely hard. You probably shouldn't even attempt to do it. So I know that I may be contradicting what I just said, but what's important for performance is to actually just report the detailed experimental setting, that everybody understands what you have done. Right? This is the most important piece. So, for example, if you look at this Gordon Bell Award, so this is Gordon Bell. If you look at the Gordon Bell Award, which is kind of you could call it one of the major awards, if not the major award in computational science today, the goal of the award is to reward a research team that has achieved a very high performance, so it's performance-centric, for solving a real-world problem on one of the largest computers on the planet. So it's an annual award. It comes with $10,000, and it's actually a high-level ACM award decided in the same structure as a Turing Award. So it's one of these very high-level awards. However, I don't think you can reproduce any of these 5-year-old results, which is quite strange, right? Because they're celebrated as very important science results, like a large award, but they're essentially non-reproducible. This is why I want to push this notion of interpretability. So if you follow the guidelines that I'm going to explain in a couple of minutes, then you will make your performance results not more reproducible, because that is fundamentally hard or even impossible, just because the systems don't exist anymore. Like the systems they ran on in 2013, the largest computers on the planet, they have been retired by today, right? For sure. And these systems were hundreds of millions of dollars worth of equipment, which means you cannot easily reconstruct them today. Actually, I would still say it's in the realm of impossible to reconstruct such a system. Even technically, it's going to be extremely hard if you had infinite resources. So this is why you want to make your experiment interpretable. You want to make sure that the reader of your paper understands exactly what you did and how you did it, and not just the result. So if you have a performance paper and you just say, my code is faster than the other guy's code, it's totally useless. It's not valuable at all for anybody. If you explain exactly why, for what detail, and where the effect of being faster stems from, that may be something that may teach something to the person reading the paper, right? And I see too many of these papers, my code is faster than the other code because I tuned some XYZ. So that is something that you need to keep in mind. Okay, so now let's get to the fun part. So we are all interested in high performance computing. We want to see it as a science. That's what I'm assuming here. The problem is now, if you're a scientist, so you may be a domain scientist, so non-computer scientists, but if you observe computer scientists, how they measure performance, it's a bit of a disaster. So how do you measure performance? You measure performance, well, somehow you measure. But the question is, how many iterations do I run? How many measurements should I run? And once I have the data, how do I summarize it into a single number? How do I compare different systems? How do I measure time in parallel systems? These are all questions that everybody answers with an intuition. Like usually my young students come to me and it's like, oh, I did like 1,000 measurements. Is that enough? And then I'm like, well, how do I know? And this is why we establish these principles that follow to answer these questions. You will find answers to all of these questions. I'm sure each of you has asked at least one of those questions when running any performance experiment, because it's at least the first one, right? So what should you measure? And this is a bit of the problem. So we actually looked at the state of the art in the community. So we looked at 3 top class conferences, HPDC, PPOP, and supercomputing over various years with a random sample of the things. And at the end, what we basically found after looking at 120 papers, don't look through all of this thing, we found that most papers give you a lot of details about the hardware. However, they don't give you enough details to ever reproduce the thing, so it's kind of useless. So they give you stuff that you don't really know how to deal with. The average paper is very easy to question. So in the sense that they don't give you enough information to actually make it bulletproof. And unfortunately, the state of the art is bad, basically, in terms of interpretability. And unfortunately, over the years, you would assume that it gets better. No, there is no statistically significant evidence that the state of the art is improving, at least from 2011 to 2014. So that's a big problem. And again, we have to be very careful in our field to remain or to improve the state of the art. Okay, so what does this now mean? Many people have given talks like this. Right, so we know, many of you know the 12 ways to fool the masses. Who knows this? So this is Bailey's kind of old work, where he was so upset at the high tide of the parallel computing industry, so upset at various vendors apparently that came and tried to sell stuff with the most horrendous arguments, that he had to write a paper about this, how to not present any performance results. Then later, there's a very interesting one by Jose Amaral, a good friend of mine. He looks at actually non-anonymized versions of some papers. It's quite funny to see some top-class conference publications and authors exposed, let's say. And then later, Gerhard and Georg Gerhard was here yesterday at this talk at ISC about like, an extension to the 12 ways. So, unfortunately, these things are all destructive. All these talks tell you how to not do things, but nobody tells you how to actually do things. And so we try to fill this gap. So we have these 12 rules, and the number 12 is also kind of randomly chosen, that basically explain how to do things correctly and not just how to not do things. So give you a guideline for experimental setting. By the way, all of these rules are illustrated with real-world examples. So the data in these things are either measured by one of my students or taken from other papers that are anonymized. So all of the problems that I show you actually happened in practice. So they are not made-up examples. And so Garth and Eddie are the 2 people. So this is Garth and this is Eddie. So this is me, the professor, and this is the student, the cool student, and this is the professor, exactly. So we'll see. So basically, the most problematic issue is actually the issue we just discussed with the speed-up plot. The speed-up plot has an issue. It's actually way 1 or 2 in Bailey's 12 ways. What is the problem with the speed-up plot? Well, the issue is if you don't have a baseline to compare to, you can report arbitrary speed-ups. So if you have an arbitrarily bad code, and I can achieve an arbitrarily high speed-up over a bad code. It's true for any relative measure. So for example, if I want to present a very nice matrix multiplication, I just compare it to the 3-line implementation in C. And then I get a speed up of 1,000 to 10,000x, but I will never tell you that I'm comparing it to the totally trivial implementation. I will just say, well, I achieve a speed up over this other implementation. This is why this plot is kind of, it's not that bad, because we are comparing the same implementation. However, it's still quite bad because that implementation of the solver could be a really bad, not representative implementation that benefits from using non-blocking collectives, while a good implementation of that solver would never benefit from non-blocking collectives. Right? So this plot is bad because it doesn't tell me how fast the solver is actually running in absolute terms, whether the solver is reasonable at all. It just tells me that adding non-blocking collectives to the potentially totally unreasonable solver makes it faster. Okay? That is a very little knowledge. Okay? So if you now look at these papers, I like the statistics. So we had these 120 papers, right? Interestingly, 39 of these papers reported speedups, and more than 30% out of those did not report the base performance. So these are the top class conferences in HPC. Right? So it's quite problematic. In fact, it's quite funny because people rediscovered the whole thing in the big data universe. Very funny is Frank McSherry, who took this laptop and beat, I think, 100 nodes of the Amazon cloud on a graph problem. Because if it's all about the speed up, right, you can make things very scalable if you start very, very slow. It's usually very hard to scale highly optimized code. It's very easy to scale really badly optimized code. And that's a big problem in parallel computing, in the parallel computing community. So it's a very old one. So basically, you want to follow this rule. When publishing parallel speedups, you have to report if the base case of the that you use, because it's a speedup, is the best sequential execution. And ideally, you report some measure of optimality for that base case. So we'll get to this later, what this means, measure of optimality. So, and you want the absolute execution performance. This generalizes to any ratio. Right? If you report any ratio, you should report something, the base case, the base price. So you could also say, well, if I'm giving you an 80% discount on something, it doesn't mean anything. Because I could charge 1 million euros for my Apple, I give you an 80% discount, and then my Apple is only 200,000, right? So you still wouldn't be buying it, right? You need a relative, so you need an absolute number to hook to, basically. Okay, so this is rule number one. The second rule is actually from a compiler paper. So let's say you have a new compiler that you develop. One of my students developed a new compiler, and I'm asking, it runs it for these NAS benchmarks. So you probably know this, the NASA benchmarks are quite old, quite impactful. They have a large number of different benchmark codes, and we have these three compilers, ICC, LLVM, and the new compiler implemented by Garth. So we have CG, LU, and EP, and we see that if this is the performance in gigaflops, that we see that it performs better, the Garth compiler, for all these cases, better than ICC and GCC. Great, but now the question is, how does it work for FT and BT? And we contacted the authors of this paper, and they basically tell us, yeah, it didn't work for these cases, but we didn't include it in the paper because it was not what we wanted to show. And it's like, okay, what do you want to show then? You want to show that for some cases you're better, but that is close to not being very honest. Okay, so if you actually do this, basically you get to this rule. When you report a subset of experiments, you should have a very good reason for this, right? And there are standardized benchmark things like the NAS benchmarks to exactly avoid subsetting, right? If you run the spec benchmarks, for example, you must use all benchmarks to get your spec number, not just one. That's a rule. However, in the NAS, you can pick. It's not a rule. In science, nothing is a rule. You can write the paper how you want. But you should see it as yourself, as a rule for yourself. If there's a benchmark suite, you support the whole benchmark suite and not just the pieces that you just care about. Right? It's quite important. So this is a trivial rule. And the next one is not so trivial, but kind of well known, I hope. But people make mistakes with this very, very often. So for example, with this performance in gigaflops, but if you now include this result, this BT result, well, the thing actually gets 20% slower, right? You may be tempted to say that 20 plus 10, 20 plus 20 minus 20 divided by 4 is 10%, right? But Paolo laughs because that is one of the blunders that you should not be doing, but people do it. And the problem is you should not use the arithmetic mean to compute ratios. Right? That is total nonsense. Okay, but now you may say, well, use the geometric mean. Right? That's the obvious suggestion. Can anybody explain what the geometric mean means? Can anybody explain how it's defined? You multiply them together and take the nth root. Right? It's still kind of weird. Because the problem with the geometric mean is that there is no clear definition. I have no intuition what that really means. The arithmetic mean is very obvious to me. I have 2 apples and some more apples, and divided by the number of apples, that's my share. Right? So by the number of people, that's my share. The geometric mean is not so easy to interpret because it lives in a multiplicative space. So the problem is exactly that the geometric mean leaves you really badly alone if, for example, for these benchmarks, some run longer than others, because then they become more significant in the arithmetic mean than others. It means, like, if I have a really big apple and a very small apple, and I take the geometric mean of the two, I will get a not so great distribution of the apples. Right? If I take the arithmetic mean of the size of the apples and not the number of the apples, then I will actually get a much better mean. Right? So this is quite complex. So it's quite obvious that you shouldn't be using the arithmetic mean to summarize ratios, but it's also not so obvious that the geometric mean is a good measure. The geometric mean is a good measure under some circumstances, but these circumstances are hard to define. For example, if you can guarantee that all these benchmarks run exactly the same time, then the geometric mean is a good measure. However, whenever do benchmarks run exactly the same time? Not in practice. So then it becomes very questionable. So basically the 2 rules derive. This is that you should use the arithmetic mean only for summarizing costs that have a direct meaning to you, basically. Right? That have a direct meaning in the real world. There's also another mean that's called the harmonic mean if you want to summarize ratios. So cost per something, right? Cost per watt or something. You should use the harmonic mean. And the definition of the harmonic mean is just 1 over the number and then something. So summarizing ratios you shouldn't be doing at all, actually, because it's not clear what that means. If you really have to summarize ratios, you can use the geometric mean, but that's only if you have to. So interestingly, out of these 120 papers, 51 papers used summarization to summarize something, right? It's a very common technique. And only 4 say which mean they actually used. So for many of those, it remains unclear what they actually did to get to the final number. They could be completely wrong, they could be right. We of course hope that they're right, but they could still be wrong. So it's very important that you actually define how you summarize numbers. You should use the terms arithmetic mean, geometric mean, or harmonic mean to describe what you use to summarize these numbers. Right? So there was only 1 paper that correctly used the harmonic mean. It's a very not so well-known term. Many others most likely used it wrongly, but they don't give you the data, so you don't know if they used it wrong. Right? So it's like, it's really not clear. 2 papers used geometric means without reason. Both of them were kind of funny because they were kind of bragging about the fact that they used the geometric means, like, hey, we know the geometric means, see, that's what we do. But there was really no reason to do it. So they could have easily used the arithmetic mean. And there are actually lots of examples in Amaral's report which have the same thing. The only real piece you can say is that the harmonic mean is smaller than the geometric mean and is smaller than the arithmetic mean. This is the only hard mathematical statement you can make about the relationship of these means. Okay? So sometimes it was actually described to me that the geometric mean is the more fair mean because it's smaller than the arithmetic mean. This was always used in the context of flops per second. It's true. It's more fair because you get the slightly lower flops per second. However, if I'm now talking about energy consumption, it's the exact opposite. Right? So you can use this relationship smaller than to your advantage if you want. Right? So this is also a lot of tricks that you can play with this. So I would not recommend using things like fairness also as an argument for choosing means. You should use technical reasons. And the only 2 technical reasons that I know are on this slide. Okay, good. So now comes a more involved, more complicated example. So we have a supercomputer in Switzerland. That's the Pitts-Stein system. There's a small partition that's called Pitts-Dora, which doesn't exist anymore, but at that time it was called Pitts-Dora. Just imagine Pitts-Dora equals Pitts-Stein. That's Europe's largest, Europe's LinPack performance fastest computer. We can argue what that actually means. It's a big system in Switzerland. So if we measure the latency, it's 1.77 microseconds. So I told my student, measure the latency. He comes back with this number. And I'm like, you know, how do you measure this latency? Why do you come back with a single number? Did you run a single experiment and it got you 1.77 microseconds? No, of course. Student is clever and tells me, I ran 1 million repetitions because it's quite cheap. Right? 1.77 microseconds, 1 million times, like 2 seconds. Sure, no problem. I can wait 2 seconds for my benchmark. But then let me look at the data. So if we measure this, these are the 1 million samples and the time observed in microseconds. Most of these samples are at 1.77 or around 1.77. Hey, but some sample is in 1.2 milliseconds. It's like nearly a factor of 1,000 slower. So there is something happening here. There are many other samples that are much less. So somehow this statistic is all lost in the summarization of these samples. So now you're wondering, is there more to this data than this 1.77? Well, first of all, you should never just say it's 1.77. You will see why in a couple of minutes, because it's not 1.77 on that system. 1.77 is a latency you will never see on that system, in fact. So you should really say whether your measurement results are deterministic or not. So in this case, it's clearly non-deterministic. Deterministic means repeatable. So basically, you would measure the same number every single time. There is a very small number of real computer systems where performance measurement are deterministic. And these are hardware systems where everything is just clocking the same speed. On a real computer like this guy, it's a total mess. If I measure a time twice, I will never see the same number, unless my timer is very low resolution. So, okay. So interestingly, most of these 120 papers, they have non-deterministic results. So only 15 measure some variance, or mention some variance. We already gave them credit when they said there was little variance, for example, or the data was mostly consistent. That we already counted as saying something about the variance, right? Only 2 report confidence intervals, which is a statistical tool to use. Both of them are wrong. We will see this in a minute. So actually, you should look at confidence intervals. So who knows confidence intervals from like the basic statistics class? Okay, if you don't know this, you need to look this up. But you need to look the ones up that I will tell you, because you most likely know the wrong ones, unfortunately. Because the non-parametric ones are not taught much in today's basic statistics classes. Okay, so actually what you can do, and what's even cooler, if you know confidence intervals, so basically a confidence interval has this very convoluted definition. I don't want to repeat it because I'm most likely saying it wrong, because there's this very notchy definition of how to exactly say it. But somehow it gives you a band where with an infinite number of repetitions, I believe with a very large number of repetitions, most measured values will be in this band with a certain probability. And by most, this is like the probability of the confidence interval you define, like 95%, 99%, 99.9%, you choose this, right? So this is actually quite cool, because if you now come to me and ask the question, how many measurements should I do? Then I just say, well, you know, you measure until your measurement result is within a certain range of a 95% or 99% confidence interval. And then you're fine. Then you stop measuring, because you have that's what the confidence interval is good for. Right? You don't run 1 million measurements. You can run 1 million measurements, and hopefully you are within that interval, but you can stop earlier if you hit that interval, especially if your measurement is expensive. Right? So that's the thing I'm going to talk about in a couple of minutes, so in case you didn't get this now. So basically what every paper should say, if you want to report a single number like 1.77, what you would say is you report this number and you say, we measured until the 99% confidence interval, or say 95 or whatever, is within 5% of the reported mean. And the mean is then this 1.77. Then I know that you have a statistically sound measurement methodology, assuming you use the right confidence interval. You should probably say non-parametric confidence interval here, because you will see how you can be fooled for that particular result. Okay, so now this guy is clever and says, oh, I looked up in my textbook what a confidence interval means. He looks at the equation and he computes the confidence interval for the data he measured. And then he says, oh, it goes from 1.675 to 1.775. Screw you. 1.77 is exactly in the middle of this. Wonderful, I got the perfect confidence interval. Okay. The problem is what the textbook doesn't tell. It tells you at the the third page, probably says, well, for all the following statistics, we assume that the data is normally identically distributed. And then they never mention it again. And then somehow the Garth did the computation assuming that the data is normally, and IID is the term, right? So the problem is in performance measurements, is the data normally distributed? Well, but he's clever because he says, wow, you know, I know this. So I use the central limit theorem to subsum my data, a standard statistical technique. So who knows the central limit theorem? No? What does it say?
Every distribution sort of approaches to the normal distribution.
If you sum it up. If you sum it up, any distribution approaches the normal distribution asymptotically. That's the problem. It may actually take an infinite number of sums to get to a normal distribution for some very ill-defined distributions. So he subsummed a size of 100 and assumes it's normal, which is nonsense, because if the distribution is bad, it'll not be normal after subsumming with any constant size, right? Okay, so now we do a normality test, and this gets a little bit more into statistics. So if you look at the original distribution here, you see that this is not normal. You see it has a very long tail towards the right, which you don't even see on this diagram, but there's a lot of stuff here, right? You also see that there are kind of two peaks here. Here's one peak and there is one peak. You could now say I log normalize the data, it doesn't get more normal. You could now say I subsum the data k with k equals 100. Oh, voila, the central limit theorem kind of works, right? It looks more normal than before, but it still has a long tail, so it's not normal. If you subsum it with 1,000 subsets, then it looks more normal even. The tail gets shorter, so of course central limit theorem is correct, right? But it's still not really normal, and you can see this in a so-called quantile or QQ plot. In the QQ plot, you plot the quantiles against each other, and they have to be on a line for a normal distribution. You see it gets more normal towards the right, but on the right side it's still not normal. This is not underlined and this is not underlined, the quartiles. So if you want a statistical tool, you do a QQ plot and check whether your data is normal. Most likely in computers, in performance, it's not normal. Why is this? Well, it's relatively simple. Because if the data was normally distributed for a performance measurement, then it would mean that my computer was equally likely to get faster than it is to get slower. And that's of course not true, because my computer is usually fast and with some probability goes slower because there's some other program running or some effect. Right? It would be really bad if it was normally distributed. Yes?
What kind of network is this computer?
It's an Arias interconnect. And it's a Cray, and this will play a role in a couple of minutes.
Because then it won't be normal anyway.
It's not normal at all. Yes. So, but these are real measurement results from that computer, right? Okay. So we'll see. You'll see. I'm sure you'll enjoy this. Okay. So if you now assume that the data is not normal, and you apply a confidence interval that's called the non-parametric confidence interval, then you will get a confidence interval from 1.6 to 1.9, wide open. And that makes you very suspicious, because suddenly I have more than a 10% range in my confidence interval. So that shows you something is wrong with the data. So remember, the confidence interval assuming normality looked perfectly fine for this data. I'm very happy that this data works out so nicely, but it actually did. It looks perfectly fine. If you would report this number, you would be happy. You would fool everybody. The non-parametric one looks suspicious. So never assume normality. It's really, really dangerous. Right? And as I just mentioned, most events will slow down performance. This will almost always lead to heavy tail distributions for performance events. Some textbooks are completely wrong. They just say 30 to 40 samples are enough, and it's like random constants. It's like, well, why is 30 to 40? And these two papers mentioning the confidence interval, they didn't say anything about what confidence interval, so they're most likely wrong. Okay. So let me skip this, because there's a way to deal with non-parametric data and non-parametric statistics, but you can read this in any textbook. I just want you to know the term. Okay, so now if we compare non-deterministic measurements, so let's say we have this variance in this compiler work. This was actually a plot from that data we got later with that compiler. What happened here is that, remember, it was 20% faster than before. Right? But they had variance, so they only reported the absolute, the mean. Right? So these are the means. The difference between the means is 20%. But this is now a so-called box plot. The box plot plots a lot of statistical information. The whiskers here, so this range, is the confidence interval, a 95% confidence interval. This is the 25th quartile and the 75th quartile, in case you know non-parametric statistics. And this is the outliers, basically. So what you can see here is that the confidence interval overlaps of these two, which means there is no statistically significant difference between the two compilers, ICC and GRAPH-CC. So that result is statistical nonsense. Right, so keep that in mind as well. If the confidence intervals if you want to compare two numbers and the confidence intervals overlap, then it means that there is no statistical evidence with whatever confidence you have specified in the confidence interval, like 99, 95% or whatnot, that the data is actually different. Right, so it's quite a strong thing for many results. Okay, very good. So now let's actually zoom into this data. I kept showing you this data from the Pitts-Knight machine. This is now zooming into the interval from 1.5 to 2.0. That is the actual distribution of the data. Here is your 1.77, this is a density plot, meaning the higher it is, the more likely it is to observe the data. At 1.77, that's very unlikely to observe in practice. It just happens to be the average of this blob here and this blob here. Right? Totally sucks. So if you would have taken the mean and the non-parametric confidence interval, you would have been completely, utterly wrong in what you report. Okay? And you would even look confident about it because you said I used the confidence interval. Right? If you use the median and the non-parametric confidence interval, here 99% CI around the median, you get the problem. So what do you see here? Does anybody have a suspicion why there are two? So remember we are measuring the latency from from A to B and back. So why there are two distributions? Yes? Yes, exactly. So we have a network in the gray areas machine that can either from a source to a destination send on the direct path, right? This is the lower latency, or it can send through an intermediate node to the destination. It's adaptive routing. So based on the state of the switch, which is non-deterministic, it's determined by the overall state of the network, right? It'll choose for each packet whether it goes the green route or the red route, the green route or the red route. It'll never be here, right? So here it only ends up with some noise that maybe. So this just shows you that you can be arbitrarily wrong when measuring real computer systems, even if you think you're doing statistics, right? So be extremely careful. So now the question is, darn, what do I do with this? I have now two values to report. I have to say sometimes it's 1.65 and sometimes it's 1.92. That's weird. How do I now compare to that system? That is an InfiniBand system, so that only has a single route, right? So that of course has a single modal distribution. How do I compare to this? Because sometimes this system is faster, but sometimes it's slower. Fortunately, there is a statistical tool that I don't have time to explain that is called quantile regression. Because for some cases, again, as I mentioned, the system is faster. For some, it's slower. But you can now talk about the quantiles under which it's faster and under which it's slower. The way to interpret this in real English is you could say that this Pilatus system, the InfiniBand system down here, is better for worst case critical workloads, but worse for best case workloads, basically. So if you care about, if you're a data center operator and care about the heavy tail back here, then this is the system for you, right? If you care about the expected best time, as an HPC person typically, then this HPC system is much better for you, right? So this is getting into very subtle statistics. I hope I didn't lose everybody, but the idea is really that you need to look at the distribution of your data. So rule 8 is you actually want to figure out if measures of central tendency, basically, can I report a single number or not? Right? Does this even make sense? For some systems, it doesn't make sense to report a single number because that number has no meaning. Like the median here, or even the mean has no meaning. You see that it has no meaning if your non-parametric confidence interval is wide open. Right? That usually happens because it's pulled apart by these two modes of the distribution. You will never see it in the confidence interval assuming normality. Right? Okay, so now if you need many, many measurements, as I just mentioned before, you can use the confidence interval for measuring until it is within a certain % of the reported mean. Right? So you can actually write a benchmarking tool that uses the theory of statistics to determine how many iterations you need in order to get what's the minimal number of measurement iterations needed to get a good statistically significant result. Right? We have this all implemented, by the way. There will be a reference at the end for a library that does all of this for you if you want. And then you can pull some tricks, but I'm slowly running out of time. There are two more things I want to mention. There's experimental design, which is quite funny in the MPI environment. This is an MPI reduction operation. Usually when you look at the average paper, they give you this plot. Right? There's a number of processes and then 2, 4, 8, 16, 32, and 64 for their implementation. It's very suspicious. This is like all powers of 2. So they randomly chose powers of 2 for their algorithm. Well, if you measure the same algorithm with powers of 2 plus 1, it suddenly gets much slower. Because for these communication algorithms, you always have to handle a special case when there are not powers of 2, because then the tree doesn't fit. Right? And then they get much slower, as you can see here. There's like nearly a factor of 2. So make sure that your experimental design is honest. Right? This is not honest. Okay? If you know about this. So rule 9, and this is a very fuzzy rule, you need to document all the varying factors very carefully, and you need to choose the varying factors very carefully. So your experimental design. There are books on experimental design. So this is a single rule summarizing like 1,000-page textbooks. So this is very, very fuzzy. So we recommend factorial design for all kinds of things that you can also look up online. So then the time in parallel systems, that's actually even a story that I don't have time to show, unfortunately. But it's even funnier. You can be arbitrarily wrong measuring times in parallel systems. So for example, for broadcast implementation, if you measure it like this, for I equals 0 to I 1000, this is, by the way, from the Intel MPI benchmark. So this is kind of the Intel version of the benchmarks. Complete nonsense if you implement a broadcast like this, which basically sends from process 0 to 1, from 1 to 2, from 2 to 3, from 3 to... So you send a chain, right? This means that you have a latency of n operations to get to the last. However, you start the second one after one timed step. And then you start the next one, the next one, the next one, the next one. So if you run the loop like this, each process will basically immediately start after one time step, and you will just pipeline all the messages nicely through, and you will get a constant time broadcast implementation, which is theoretically impossible, but you measure it because you just measure this down here. You don't measure the actual latency. What you would need to do is you would need to measure the broadcast, and only once the last one is finished, start the next broadcast, which is quite hard to do in practice. It's possible. There are papers on this. It's called windowing broadcast measurement windows. So something that is, you need to measure the operations separately because pipelining is a valid effect. Then summarizing times gets even more complicated. So basically, if you measure the times at different processes, you will get different times. Usually people only measure at process 0. However, that may be as wrong as the previous plot. So now the question is, how do you actually do this for a distributed system? Not so simple. Many different ways to do it. However, you should exactly specify what you do, how you sum it up. Because I cannot give you a general rule how to do it. But if you don't tell me how you measured the time in the parallel system, I do not know what your measurement result even means. Right? Very important. Okay, so then let's skip this. So this is just bounds, and the last one is basically there are very nice ways to plot statistical data, and I want to show you 3 different plots. One is called a box plot, which this is usually plotted as a single point. But if you have a distribution, you can use the box plot to plot it in a way that you get all kinds of statistical information, like the first quartile, the fourth quartile, the mean, the median, and the confidence interval in a single picture. Right? These are extremely informational. Even more informational is the violin plot, because it plots you the whole distribution. Right? This is what we've seen before, just like upside down. And then for symmetry reasons, they do it on both because it looks stupid if you have it only on one side. So that's called a violin plot because it often looks like violins. But it's very nice. These are very nice plots. And you can even combine the 2 plots, box plot and violin plot. So there's a plotting library, a plotting package in R that you can use that does this beautifully for you. Also, the PyPlot library does this beautifully for you. So there are many ways to show the information you actually have in your data to the reader and not just keep it for you and then give the reader 1 point. Okay, so plot as much information as you need to interpret the result. And the distribution is very often very helpful. So with that, there is a whole paper on this if you're interested. So if this was a bit too fast, or if you want to look at the rules again, the scientific benchmarking of parallel computing systems actually specifies this. It also explains how to do all the statistics in only 10 pages. So we try to make it as short as possible, not that you have to read textbooks, but if you read these 10 pages, you will get a basic understanding how to do correct benchmarking without reading the 100-page textbooks. By the way, it references 100-page textbooks. If you want to know about all the statistics and everything in the background, you can. It's a good start to find all the related textbooks. So we hope with that to make a bit of a difference in performance reporting and improve the state of the art a bit. And with that, I want to mention one last thing, that we have much of this implemented in a thing that we call libscibench, which we maintain at our lab, that makes it easier to collect these numbers and automatically do timing on parallel systems, benchmarking on parallel systems, and produce these plots in a simple way, because sometimes the plotting tools are not so easy to use. So with that, thank you very much, and I have like 2 minutes for questions. Very good.
Yes, everybody's exhausted.
Yes, I can imagine.
It's good for you to catch a cab.
Yeah, exactly. That's
Maybe Torsten, can we just argue about your first plot when you said that our argument, you said raw timings are better than speedups.
yes.
It presented a number of processors versus timing.
Yeah, it's very hard to read
Yeah,
this
that
curve. Yes.
is meaningless, right?
Yes, yes, yes.
That was my even worse.
Yes, in that case, what I would recommend is you plot the speed up, but you annotate the base case with the absolute time.
Sure.
And that's the better way of doing it. And I'm doing these time plots, yeah, this is horrible. I completely agree. And actually what you should be using, this is what I had to skip unfortunately, what you should be using are bounds plots. You should say, what is your theoretically achievable maximum? Plot that, like the roofline, for example. But roofline is just one example. There are many, many ways to do bounds plots. And then you know how close you are to the achievable maximum.
Will you share those slides with me?
Yeah, of course, they're on my webpage.
I'm allowed to, okay, so you can upload them.
Yeah, of course.
Thank you.